45, Julia. So just a couple of seconds and then we can start.
Great. Thanks very much. Thanks everyone for making your way over from the wonderful keynote. I'm going to present the results of this year's 7th annual Julia User and Developer Survey. So this year we completed 721 interviews online among Julia users and developers. That is an increase from last year, but this year and last year both represent a decrease from previous years. Our participation went up to a high over 2,000 during the dark days of COVID. And we are investigating some options to increase participation in the future. The ways we recruit people into the survey, we post messages on Slack, Julia Lang Slack, Discourse, through social media channels, including X and LinkedIn. We send out emails from Julia Hub, for example. We have quite a large email list at Julia Hub. And we post at the top of the page on julialang.org, juliacon.org, and juliahub.com for the period of fieldwork, which is this year was June 18th to July 8th. We offer the survey in 6 languages: English, Simplified and Traditional Chinese, Japanese, Korean, and Spanish. Many of the survey questions remain the same from year to year. Where there are changes, those are denoted in the presentation with the generous use of asterisks, noting in what year the changes were made and what the changes that were made were. Every year we solicit feedback from the community about the survey. We read through and we review all of that feedback. And then once we've collected all of that feedback, Viral Shah and I spend an hour or more reviewing each comment and deciding what modifications to make to the questionnaire. So if you've offered feedback in the past, it may have been incorporated. If it hasn't been incorporated, I can assure you that it has been reviewed. And if it wasn't incorporated, some of the reasons we don't incorporate feedback include desire to have standardization year to year so that we have trends that we can follow over time, as well as complexity. And also, feedback that shows up year after year is more likely to be included in future iterations of the survey. So if you look just below the title bar, you can see in italics the exact language that we used in the survey. So the question we asked was, which of the following languages have you used regularly or frequently during the past year? Julia use continues to climb among Julia users. So this is among people who are using Julia. The percentage who say that they've used Julia regularly or frequently during the past year has increased. So we would expect it to start high, but it's been getting higher and higher. And what that suggests to us is that more and more Julia users are using more and more Julia for more of their work and less of other languages. Many of the other languages have been declining. We saw a big decline in R this year, for example. And over the past 2 years, we had seen an increase in Rust usage among Julia users and developers. That seems to be perhaps have leveled off, plateaued, or may even be tailing off. And that is reflected as well in the next question. So here you can see the previous question we looked at, which of the following languages have you used regularly or frequently during the past year, as well as the follow-up question, which of the following languages do you plan to use regularly or frequently during the next year? And you can see these compared. So if we look at MATLAB, for example, 14% of Julia users said that they used MATLAB regularly in the past year, but only 8% say that they intend to use MATLAB regularly or frequently during the next year. Rust here is still increasing a bit. So 8% said that they used Rust during the past year, 11% say that they intend to use it during the next year. R has increased as well. And so, this may be a temporary dip that we've seen in our usage, for example. We'll see next year if the stated intent to use our tracks with the actual reported usage. We ask, how much do you like each of the following languages? And we give them a very long list. I've shown only Julia and Python here because those are by far the two highest. So 96% say that Julia is one of their favorite languages or they like Julia. 83% say it's one of their favorite languages. 13% say they like Julia. And Python has been declining over that time period fairly steadily. We asked folks, what are the most popular technical features of Julia? Number one continues to be speed and performance, followed by ease of use, package design, open source, multiple dispatch, et cetera. And there's a long tail of other responses. The most popular non-technical features of Julia include number one, that it is free, followed by the Julia community of developers. First, that the community of developers is talented and active, and then that the community of developers is warm and welcoming. Easy to create packages is also in the top four. The biggest technical problems, number one is slow compile times. There's a lot of discussion after last year's survey about this, led by Tim Holy and Jacob and a few other contributors. And it seems that the consensus is that this is more about pre-compilation. When we talk, the second part of this is, for example, it takes too long to generate the first plot. So Tim has suggested that we might want to alter this option, this answer choice, which I've discussed with Viral, and we may make some changes to that for next year. Thinking about the non-technical aspects or features, what are the things you like least? Number one is there are not enough Julia users in my field or industry. So adoption continues to be a concern. Leading platforms where Julia users and developers interact, number one and number two are GitHub and Discourse. Followed by Slack. YouTube has declined a bit. Stack Overflow has been declining significantly over the years. X, formerly known as Twitter, continues its decline. Discord has also taken a bit of a dip. Which of the following best describes your use of Julia? So number one is research, hobby programming, and individual work, followed by using Julia for development as part of a team, for teaching, production in a business critical task. This is a new question this year in response to feedback from the community. How many PRs did you submit to the Julia ecosystem in the past 12 months? The majority have submitted at least one PR in the past 12 months. And it will be very interesting to see how this number changes and grows. When did people start using Julia? So the largest number started using Julia between 2018 and 2022. What percentage of the programming work you do is in Julia? At this point, the majority of Julia users and developers do more than 60% of their programming in Julia. How robust is the current Julia package ecosystem? The majority say somewhat robust. 80% say either very or somewhat robust. And there's been a decline in the percentage who say not very or not at all robust. What editors or IDEs do you use frequently? Number one is VS Code, followed by Vim, NeoVim, Pluto. Jupyter has declined. What types of AI assistants do you use with Julia? Number one is ChatGPT, followed by GitHub Copilot, and then Claude. The percentage who say none of the above has declined precipitously over the past couple of years, from 68% 2 years ago to 52% last year and 40% this year. What cloud solutions, if any, do you use together with Julia? About half use one or more cloud solutions. Among those, the number one choice selected is a local cluster, followed by Google Colab, Julia Hub, AWS, Google Cloud. How did you download and install Julia? Julia Up continues to increase. 79% now say they use Julia up from 66% last year, 37% the year before. Looks like I will not be able to make it through all the rest of my slides. These will be available online, and I am available to discuss after this as well. I will note before leaving, professionals make up nearly half of our survey respondents. Academic users make up just over half. Again, people can respond, can give more than one response here. And among professionals, the most common industries include software, IT, and engineering. Number of years, there's been an increase in the number of Julia users and developers who have more years of experience. I can? What's that? I have 20? Oh, okay, then I'll go back. Okay. Oh, that's okay. Thank you. Thank you.
Does anyone have any questions? And if not, who's the next speaker? Don't have the next speaker? Yeah, okay. In the meantime, does anyone have any question? We have time for one question. I do have a question. Do you have any type of demographics? For instance,
Yes.
which kind of country is the one that uses the most?
Yes, so the largest number of participants always come from the US, and then following the US, there's a significant number from Western Europe, but we have representation from typically 60 or 70 countries all around the world, all regions. Yeah. It will be posted on GitHub, and the video, of course, will be on YouTube. It is on GitHub. Okay. I think it was added in the last few weeks.
Yeah, so we have our next speaker. Please take it away.
Hey, good day. What do I see here? Exactly. Yeah, this is about an own concept about meta lines, embedding them in comments. Actually, in my proposal, I said I'm just using a package to introduce the concept. However, I had the glorious idea to actually start adding some things in my talk yesterday evening. So yeah, let's see how we go. Just quickly an overview. We have just to think about it, why metadata opposed to normal data, why embedding it in comments. I promised a schema in my proposal. We'll see about that. And then, yeah, learning by doing, having a quick look at some examples, and then the rest we'll see how it goes with the time. So, why metadata opposed to normal data? Well, it's about interlinking all possible data. Every data needs to be in context. Data by itself is not much worth, and we have a lot of useful data, but if you put it in context, it makes a lot more sense often. It really gives you a whole web where you can link in. This one here is a really important one, weaving webs of interlinked atomic data units. So I really want really small data units. I don't want files. I want to interlink a lot of different stuff. It can be large, big, whatever, information, but linked. Hierarchies are used everywhere. It's obvious. why. It's very easy. You categorize the whole lot. Also computationally, it's advantageous. We have it in folders, digital and otherwise, in computer science. But it has its disadvantages because very often it actually does not really match reality. It really restricts us. Our brain does not. I think if our brain worked only with hierarchies, we wouldn't be where we are at the moment. I think we wouldn't have made it to the caveman stage. So that's what I'd like to do a lot more in the computer. Actually, I want to almost get away from the explorer and have a completely different take at data. So embedding it in the comments, well, there is one obvious advantage. As soon as you have it in the comments, you can actually always use the same kind of meta language. The parser just needs to be able to look in the comments of the different languages. Of course, if you then work with that language, then you need to write different packages a little bit differently, but you can actually use the same thing. This is very important. In fact, you can even put it in a Word document, run that thing over it. The idea is that you actually have, it takes all the little data out, and at the end, it can actually save it somewhere else and use it again later on in other documents. A little bit like brain cells. Yeah, the schema, it's kind of work in progress because it evolves as I realize what is necessarily or what is not, these kind of things. I don't have a ground plan. Now, I have some objectives that need to be satisfied. It needs to be intuitive, succinct, powerful, that's obvious, and all these kind of things. And especially, I want it to be extremely extendable later on. There is the pang is something I introduced just recently, and I wanted to show that today, but that was a bit too risky. Well, we'll keep that in mind when we go through the thing. So if we look at literate, it starts with a source file, and out of the source file, it can start making all possible other files. Notebooks, standard, Markdown, Documenter. Today we're going to use Documenter, if I have the time. Here we kind of see the workflow of that one. This one here is literate. We just have chunks of text and chunks of code. And that's how everything gets chunked up and then worked with it. Here, I briefly show, you have your text chunks and things, and the parser is going to recognize that. Now, the big difference with Go Literate is just to show the concept, actually, of that metadata. It's not really my final destination of it, but yeah. With the metadata, I want to be able to use Documenter or those kind of things a lot more in a powerful way. So you have a metadata, hierarchies. We talk again about hierarchies. And with very little code, can you achieve a lot. So just bear with me here briefly. For instance, we have here a height. So this will be a meta line. It's a baby meta line. It's a baby example. Now, here we can see that the height itself disappeared, but nothing else disappeared. These are only baby examples. You can see how this changed in the markdown, and then in the output it is gone, right? At the top, usually I wouldn't show that. That is for the file level, because you have a whole hierarchy. So you can set it on file level, user level. You have, we'll see it in a sec. So what happens if I put this one here down, like this one here? Now I call that attached. It's a little bit like with the doc strings. From here on, all the things that are attached to it will actually also react. So they will be hidden here, for instance. As you can see, it's gone in the output. These are just examples to show it. I mean, that's not difficult to do. More interesting is actually this with inheritance and meta hierarchy. Hierarchies are, after all, useful. Ooh, 1 minute. Yeah, well, so you would have a whole file here, basically, and you have this one here. Here you see how it inherits. So the height gets passed on. Also, if you see on top there, the height is called, it gets automatically written into visibility. That's a type. Yeah, so it goes on. Here, yeah, that's all autocompletes. This is a type. That's what I wanted to show. So, what seems still important, you can maybe see it the best when we actually get here. So you can actually just write the title in the meta line, and then it automatically starts making titles like this one here. Of course, that's nothing groundbreaking. We could do that for 50 years. It's more the idea, it captures it, and then it can store it away, and it will take the whole other data away with it. And there's a whole interface now that you can start using literate or Go literate in a completely different way. It has bit vectors for it, a whole interface with, yeah, alterants. Just very briefly, following categories, the idea is then actually to have plug, absorb, and go functions. These are the functions I have for Go for Documenter. That's not really what I have implemented. It's too easy, but yeah. No, I mean, you said I'm basically out of time, right? Yeah.
Sorry, we have to continue with the schedule. Yeah. Please, a round of applause for the speaker. In the meantime, the next speaker can set up. Yeah, thank you. Does anyone have any question for the speaker? Yeah, I do have a question. When you mentioned that this meta document can be linked to Word, like the app, do you do that manually or do you do that automatically? Is there any way to link it with Word?
With Word?
Yeah, with Word. Like, you know.
Well, no, I mean, and those things are just in any document. And maybe you're not even going to see it. It's going to hide, but it's going to, you can basically use it in whatever thing you want. In Word. Yeah. I understood Word. Yeah, you can put it in Word. You just need the program to run over it, and of course, then in the final document, it's gonna extract it. It's gonna, I mean, because you're not gonna pass on that thing. That's yeah. Yep.
All right. Please Let's continue with the next speaker. And yeah.
Yeah, thank you. So my talk is about shipping Julia, shipping your Julia app in an air-gapped environment. Let's learn what an air-gapped means exactly. So air-gapped is a closed environment where you don't have access to internet. That's the layman explanation of it. You basically don't have access to any external network as well. Getting things in and out of air-gapped environment is really difficult, and it only goes through authorized channels. So internet is not one of them. And most of these air-gapped environments are used by secure computing environments, like defense, or a company which doesn't want to share its inventions with the world and wants to safeguard it. I mean, many enterprises do have secure computing environments, and they do use air-gapped environments. So it's pretty common. It's not all that unusual. We do have plenty of enterprises who do have air-gapped environments, along with the government and defense, of course. So moving on, you will face a lot of challenges while deploying your Julia app in this kind of environment. You see, your Julia app, if it requires, your Julia app cannot update its registries, it cannot download packages, it cannot download artifacts, it cannot download anything. Basically, it cannot build on its own using the resources of the internet. And the second is, like, if your Julia app requires validating license, let's say you're using a commercial app and the user has to provide a key file or a key code just before using your Julia app. So this is kind of tricky in an offline environment because your app is not able to connect to internet, and so your license server is centralized on the internet. So it's kind of difficult to validate your license on here as well. And if people have noticed, while installing few softwares on Mac, you might have realized the gatekeeper just stops you saying this package is not notarized, you cannot go through. And Mac, when you install a software on Mac, the Mac actually checks with the Apple server whether the software is notarized or not. So this cannot happen in air-gapped environments because the environment doesn't have access to internet. So you need to take care of this as well. And of course, the last one is the critical one, which is updating your app. Let's say you have given the version 1 to your end users, and you have a version 2 now. And getting things in and out, like I said, getting things in and out of air-gapped environments are challenging. So you need to think forward as well while creating your app. So let's see how we will solve these challenges in here. So the first step is never assume. Never assume. If your Julia app requires some pre-configuration that end user has to perform, and if it requires some libraries that the end user needs to install, don't assume the end user is going to do that. Do it yourself in your. If it is minimal, just do it just bundle it in your binary, and take care of these configurations and prerequisites if possible. And the most popular way to deliver in a software, a Julia app right now is shipping it in a sysimage. If you're going this work, of course, there are multiple ways. You can just create a binary out of your project, if it's Julia project, and you can give the binary as well, standalone binary. So, but the sysimage has been delivering it through the sysimage has been a popular one since years. So. If you're delivering it through a sysimage, in the sysimage you create your Julia app is compiled into a sysimage, and you ship your Julia binaries, artifacts, and everything that's required to run the sysimage on the end user system. So you need to take care of all those things, and you need to bundle every prerequisite in your binary. So never assume end user will have anything like I said, the prerequisites installed. So yeah. And don't assume the environment will be a single user or multi-user. Most of the enterprises, it will be multi-user. So what happens is like an admin installs the software, and the non-admins will use them. That's how it works in most of the enterprise environment. So the end user wouldn't be able to install their own softwares. So you need to take care of these scenarios and never assume a single scenario in there. So that's one way to take care of it. And licensing and stapling. So if your software is a commercial one and you require licensing for it, so what the most popular way is to go with a private license management license management service like License Spring. So you integrate these license management softwares in your init. So as soon as the user starts the project, starts your Julia project, your init should check if there is a valid license in there or not. So that's one way to do it. And since you're offline, your license management server, your license management solution cannot contact the licensing server. So you need a floating license for these situations. And you need to take care of clock. If you're not using some license management like License Spring and you're implementing your own, you need to take care of clock tampering as well. Like the user can set their clock to some predate, and I mean most of the offline licenses works based on the time. So clock tampering is a very common way to get around it. So you need to make sure your software is clock tampering proof, anti-clock tampering proof. So you need to store the timestamps in your software, but there are multiple ways to do it. And of course, the most popular way that enterprises use is set up a local license server. So this license server will have, you would give licenses to this license server, and every user will locally connect to this local license server and validate with the license. This is one of the most popular way that people do as of now. It's used by enterprises lately. Stapling is one way to get around the Mac installation issue that I talked about. If you staple your Mac binary, you don't your Mac doesn't need to contact Apple servers to validate your binary. You do the notarization and you staple the binary. As soon as you staple it, the installation of software on an offline Mac will go through without contact in the servers. And lastly, how to update your package. One simple way is have a local PKG server running. So you can push your changes to a local PKG server, and users can just do a PKG update. That should go through. That's one way. And if the local PKG is not an option, you can always bundle your updates, and your software needs to take care of the bundle, like how to read the bundles and how to update them based on that. And the last one is of course, it's been the installers have always been supporting the updates. You can give an installer which supports existing installation, and the installer will take care of it. That was last of it. That should be all from my side. Any questions?
Yeah. Does anyone have any question? So does this part take care of the user interface? You know, like the...
Yeah, the installer will take care of the user interface.
Okay.
Yeah, I mean, if you're sending the installer will take care of it. Yeah.
Okay. If no further questions, please round up us and let's have the next speaker.
Thank you. Sorry, this is mine. Oh, yeah. Sorry. I think he has one. Yeah. Yeah. Thanks. That's useful.
Do I start? Yeah. Hi, everyone. Happy to be here and give the talk on the flexi joins. This is, I think, the most flexible, most featureful package for joining tabular, non-tabular datasets. Maybe not even just in Julia, but in general. So first of all, regarding tables in Julia, to set the scope for the talk, there are kind of two approaches how people use tables. First one is kind of what came from Python and R, that is using custom container types like data frames in memory datasets. Maybe there are other packages. And the second approach is kind of unique to Julia. You can use generic collections, mostly vectors, abstract vectors. It has some benefits, familiar performance model, composability, and here I show some examples just from base functions that correspond to typical tabular operations. So regarding joins specifically, custom table types like data frames, they typically have dedicated specialized join implementations. And again, typically, as far as I'm aware, they only support equality joins. So joining by key in one dataset equal to the key in another dataset. However, there are much more join types in general. So for generic collections, mostly like vectors, there is pretty old but still working package, split apply combine.gl. I actually contributed to it a bit like several years ago. Now it's barely maintained, I would say, and it also only has key equality joins. And I created flexi joins in 2022. The aim here is to support all kinds of datasets, all kinds of joins with a performant and uniform interface. So since the release in 2022, there were no breaking changes, so it's still on the there was no kind of breaking version bumps, no breaking changes at all. Maybe there will be at some point if the current interface doesn't work out, but as of now, it's been pretty stable. It already supports all kinds of joins, like key equality, of course, A's of joins, interval joins, joining by distance, combining multiple different conditions, left, right, inner, outer joins, group joins. And the design goal that has materialized is that it's fast, as in it never falls back to just looping over both datasets and selecting matches. So natively, with just generic code, without any special handling, flexi joins support all kinds of Julia collections, abstract arrays, tuples. If you have very small data sets, tuples in inner loops can be very fast. Dictionaries, type tables, .gl, and like everything else, anything else that supports a collection interface. I personally don't use data frames, but I got a few feature requests. It's like several people requesting to add this compatibility several years ago. So I added them. We are a sync compatibility layer because data frames don't support the kind of general collection interface. So it's like basically 10 lines of code to convert them to structure arrays and convert it back the result. So in this talk, I will show a few examples demonstrating the interface of flexi joins, how to use it, and then I'll briefly explain how it works and how it's designed and what are the kind of limitations and missing pieces for now. So starting with the basic interface. So the main entry point that you generally use is just the inner join or the corresponding equivalents for left, right, and outer joins. And basically, you call it as inner join with two of your data sets and the predicate. Here, it's a very simple example. You have just two tables, table of objects and table of measurements, and you want to just match every object with its measurements and specify the by key match and matching by name. This is a typical kind of key equality join. The result is really the collection of tuples containing an element from the left side and from the right side. It is almost equivalent to this list comprehension at the bottom, just faster, just optimized. So when you think of what FlexiJoin returns, it's basically this collection. For convenience, so I typically, when I'm running FlexiJoins, I use named tuples instead of tuples. So you can name like left side and right side with some typically short single letter names, but anything works. And it makes it the result kind of easier to use, because now in the result you don't just have tuples, you have the kind of O and M the same, named the same way as you named the input elements. This is just more convenient for any kind of downstream analysis. One of the kind of neat performance features that wasn't even very difficult to have is that it's flexi joins by design. It doesn't copy your kind of data from original data set. Whenever possible, so like for basically any array, it returns views of the original data set. So J is the resulting collection from an inner join, and you see that it just contains, it's a struct array, so it contains a collection of elements from the first collection, from kind of the left side and from the right side, and they are not copied collections. They are really, as you can see, they are views of your original data. This is kind of important for efficiency if you have large data sets, and maybe with like 10, 20 columns, you don't really want to copy all of these to the join result. So after you get this kind of joint collection, there are several kind of typical ways how the processing can go downstream. First of all, if you really need a flat table in the end, not just a collection of like tuples and named tuples, you can just call the Julia function merge, because each element in the collection after joining has two elements, one from the left side, one from the right side. With merge, it will just merge all the columns. But typically, at least for me, it's not how I generally do the processing after joining, because it's very convenient to just do whatever operation you wanted next while keeping the while having the names of your left and right side to avoid any confusion. So here, at the bottom line, at the very bottom line on the slide, it's clear where each column comes from, whether it comes from objects, from measurements, or if you have some combination of those, it's really kind of makes it cleaner than just merging everything into a single flat table. So this was a brief kind of intro into the interface using the just key joins as an example. But as I said, a major part of flexi joins is supporting like a wide variety of join conditions. So, for example, this is how you would write a join by kind of like column in one data set less than a column in another data set. It's still fast. It still doesn't fall back to nested loops. You can join by distances. So most of the distances from distances.gl just work for both numbers, for vectors. When needed, so for vectors, it creates a search tree. So everything also stays performant, and it is the same syntax. You specify what to merge. Like in this example, I shows that you can merge two data sets. The same data set with itself, finding different measurements that are within some time distance from each other. There are all kinds of interval conditions. So first of all, here I also highlight that flexi joins everywhere. It accepts arbitrary functions, not just column names. So here maybe you want to create an interval specifying like, okay, I want to find measurements that are timed from my kind of reference time to the reference time plus 10. And for that you create an interval. It is from interval sets. I think the most popular package for intervals. All of these operators here are supported for intervals, and again, everything stays performant. Of course, you can combine multiple conditions. So here, it shows the same conditions that we had on the previous slide, but we add the by key name. So now it does. So before we had measurements and matched with all kinds of objects, just based on time difference. Now it is both the time difference and the same name. So all the conditions really, at least most of the conditions work together. Of course, sometimes you can stumble upon like a combination that is not supported in an optimized way, and then it will error. It will never fall back to nested loop joins unless you explicitly ask for it. So performance is saved by default. Another neat thing is that sometimes you want really all matches. So that's what you get by default. You want all matches with measurements after the reference time. Here in the example, sometimes you only need the closest, and for join conditions that have for which saying closest makes sense, it is supported as a kind of multi-argument. You specify like which data set to take the closest from, and everything also just works and works performantly. So these join conditions that I walked through, they are just available in FlexiJoins itself, but it's designed to be extensible, and it is. There are other across the ecosystem. These are the ones I know. So there is joins by just by uncertainty in the uncertain.gel package for uncertain numbers. Basically, if you have two data sets with like uncertain numbers, and you want to match those that fall within their errors. In geometry ops, they added geometry predicates, I think mostly for kind of 2D geometries where you have like some polygons that contain each other and provide some tree-based optimized joins as well. And it also didn't take, I checked on their implementation, it didn't take many lines actually in the extension. And so I'm doing astronomy. So I added the join for sky coords objects where you have like two catalogs of sky coord coordinates and want to just match them, like cross-match one to another. It also works. It also is based on trees. Another thing that is not really kind of necessary to use FlexiJoins, but I find it generally useful, is that when you kind of intuitively expect that you will get like one-to-one join, so all the matches should be unique and all elements should match. Sometimes like you run it, you check that it's okay, but then your data changes and someone adds a duplicate somewhere, and you only catch it somewhere downstream. So if you really want a one-to-one join or any other kind of like cardinality constraints, just pass the cardinality argument and it will error whenever you get kind of non-unique or non-existing matches. When cardinality is not specified, it doesn't affect the join. It will return whatever matches you have. But I find it very useful whenever I know that I want a one-to-one join, or like or 0-to-1, for example. Like so, there have to be unique matches, but never several. Yeah. So this is about kind of like the overview of the functionality. Regarding performance, so this is just a quick benchmark from a notebook that's available in FlexiJoins repo. It compares data frames, FlexiJoins, and split apply combine. Of course, it only compares key equality joins because other packages don't support other join conditions. So there are kind of several regimes for very small collections, like less than 1,000 elements or so. FlexiJoins tends to be the fastest all over the board, and this is useful if you have a join in a tight loop. This is, I mean, nothing wrong with that. Maybe you have an optimization loop or sampling loop or like some other Monte Carlo simulation and run a like a kind of short join with 100 or 1,000 elements. FlexiJoins is generally the fastest for it. As soon as we get to larger, so sorry if the labels are small, the left plot is time on the vertical axis versus the total dataset size, like sum of the dataset sizes on the bottom. Middle one is the bytes on the vertical axis, bytes allocated, and on the right it's number of allocations. So now I'm talking about the leftmost plot. At the larger sizes, both packages, like first they start being like roughly equal. At very large sizes, I think data frames typically gets faster. They have like very optimized implementation for many cases. But again, this is, so neither data frames nor split apply combine support other kinds of joins. So it's nice that with the generic implementation, we in FlexiJoins can be really well competitive with more dedicated specialized solutions. So benchmarking notebook available in the repo, you can like tweak it with different sizes and run it as well. So Then a few words on how it works, so how it's designed and how it works. Basically, this is how the join process works. First, FlexiJoin looks at the condition, kind of interrogates it, what modes are supported, basically like hash join, sorted join, tree join, but it's extensible, it can be kind of all kinds of stuff. Just that for now, it's only these three are actually used anywhere. Then it chooses one side of the join to so-called prepare it. So basically, if it's hash join, it will create a hash table like dictionary. If it's sorted, it will sort one side and so on. Then it loops over the other side of the join, for example, on the right side. And for each element in the other side, it's typically chosen to be the smaller side for performance. It finds all the matching elements in the first side and the left side using the prepared lookup. So it is really kind of efficient, and also the choice of the which one to prepare and which one to loop over is reasonably clever. Yeah, so it calculates for both matches and for non-matches if needed. It just computes the indices of matches, and in the end just creates a view based on these indices, returns a view, and that's what you get as a result. I think the most kind of, maybe not the most interesting thing in general, but the most interesting thing for those who want to add more join conditions or learn how they work. So like in the very base case, for each condition, you need to specify what modes it supports, like hash joins or join, and implement the kind of function to prepare one side of the join and like optimize it in some way for lookup, and a function to find matches in that prepared lookup. Here is like an example for sort mode, really, and for sort mode, there are some convenience functions that are generic for all conditions. So the bottom two functions there don't need to be implemented for every condition. But generally, it's very short implementation. There is nothing really tricky about it. The function names can be, function names can be improved. They were kind of just created first, and I didn't want to break stuff afterwards. And really the aim that seems to materialize in the recent, especially in the recent year or so, with more packages, with at least some packages, adding support for joining with FlexiJoins. Really, one of the aims is not just performance, but make implementing new conditions easy. So this is just another example where you add this is basically how by-distance join is implemented in FlexiJoins. It uses nearest neighbors .gl to build a tree, and then search in the tree. So it is really not a lot of code. And I promised to say a few words about limitations and what's currently missing. So I think there is nothing kind of major in my view. It works, it is performant, but there are some things that can be improved. So first of all, as I said, now FlexiJoins optimizes, kind of prepares only one side for lookup, and just purely loops over the other side. There is a flexible choice. It can depend on your condition. If you want to customize it, which side to loop over, it can be beneficial to change it from default. But sometimes it makes sense for both sides to be optimized. The most prominent example is the sort merge join in relational databases. So you sort both of your data set and then just linearly merge them together. This part is not implemented for now. The main kind of questions here are where should the extension points be for this mode. Also, for now, it uses generic algorithms, so it uses like just the Julian sort function. For hashes, it uses Julian dicts. For trees, it just uses nearest neighbors. This works great for performance, as in the performance never falls back to n squared. But special cases can be optimized more. Most notably, like there are a lot of common cases. Like keys are an integer in a specific range, or you have a pooled array with or categorical array with not too many distinct values, or kind of just small integers. This all can be optimized, and it won't change the kind of asymptotic behavior. It will still be kind of like hashing, for example, or sorting, but it can make the joining several times faster for some cases. This is actually the reason why data frames are faster, because they have a lot of special cases, so many that I think like many cases now happen to be special for data frames, but only for equality joins. So also regarding documentation, not a very uncommon issue, I would say, in Julia packages, but yeah, documentation exists. But it is kind of sparse, definitely. I don't know, like from time to time I extend it a bit, but it takes, I guess, some effort. So to sum it up, flexijoins.gl. This is the ultimate package, in my opinion, for joining datasets. Works for tables, and not just for tables, for arbitrary collections in Julia, collections of arbitrary objects. Anything works. Very wide selection, the widest I can remember seeing in any library, of join predicates, join conditions, and everything with just a uniform and performant interface. I think it is really the most feature-rich package for joining, and yeah, thanks for your attention. Happy for questions or discussions now or afterwards. Thank you.
Questions from the audience?
Hello, thanks for the talk and the package. Have you compared the performance or done a benchmark with SQLite and DuckDB?
Oh, I haven't, because first of all, kind of like, if you have a Julia table, for SQLite specifically, you probably need to somehow like load it into SQLite. For DuckDB, they can read the columnar Julia tables as is. Yeah, at least when I developed it, it wasn't the case. I don't think there was a Julia binding for DuckDB then. I think that DuckDB, I mean, for the joins that they support, they should be pretty fast. But they only support flat tables, not arbitrary Julia collections. So here it is like Julia first. Okay. And it's not just kind of like for container types. It's also like for geometry types, interval types, sky chords. It's hard to get in a non-Julian software.
Okay, thanks.
Any other questions?
Hello, thanks for the package. You mentioned support for data frames. Is that coming soon, or is that already available? And secondly,
yeah, it's been available since probably the end of 2022, and when 1.9 came out, I just moved it to extension, so if you don't use data frames, it's not even loaded. If you use it, it just works.
Okay. And,
and it is regularly tested, so even though I personally don't use it, it is in the CI and in the tests.
And then related to that, why is the, for the data frames extension, why do you have to convert it to struct arrays and then back again?
Yeah, so all the types that are kind of natively supported, they follow the same interface. They are just collection of Julian values. That's why they don't need any special handling. Then data frames has a very different interface. That's why it's, I mean, it just doesn't just work with the generic code. That's why it's either converting it to something, and struct array is nice because it's also columnar, so the data is not copied when the conversion happens. But if not conversion, how else to have this? Like,
okay, thanks.
Yeah.
Any other questions? I will make a, in the meantime, the next speaker can probably, I think, set up. You mentioned that you use designs like less and higher than. What are they for? I don't know if I follow.
So if you want to find like all matches in the second table that come after, like later in time than values in the first table, or if they fall in some interval, or you want the closest match that happens after your event. Yeah.
Thank you very much.
Is this your adapter or is this the one? No, it's here. Okay. Just want to make sure you didn't lose it like I have lost many. All right.
We will, whenever you're ready, we can start at 11.
Okay. Hold on just a sec. Oh, find the presentation. That all seems to be working. All right. Okay, can you all hear me? Okay, so I will be talking about some work I've done on automating testing and documentation generation for Dyad. So I think at least half this audience already knows what Dyad is, so I'm not going to go into that. But I will say that for anybody watching on YouTube later on, we previously referred to this product as JuliaSim, and now it's called Dyad. So you may be confused because in that information about the conference, it may mention JuliaSim. Okay, so what is Dyad? Again, for the half of the audience that doesn't know. So Dyad is our modeling and simulation platform, and part of that platform is the Dyad language, which we'll be seeing a lot of examples of. The Dyad language is a declarative language that actually ultimately generates Julia code. So the point is, it's not a programming language in the imperative sense of a programming language. So it compiles down to Julia code, and it's a declarative language, and it's used mainly to describe the structure of large-scale mathematical or engineering models. And so the analogy that you can draw is that sort of Dyad is to Julia what HTML is to JavaScript, right? It sort of complements. The two are not the same, they're not used for the same thing, they complement each other. So what exactly are we documenting here? So Dyad is, as I said, is this declarative language, and the declarative nature of it means that it's not, you don't sort of get into the Turing tar pit. You can't perform computation in it. You're simply describing entities and their relationships. And that means that we can actually do a fair bit of reasoning and inferencing about such things. And we also are capturing a bunch of information in the Dyad language that we can then use as part of the documentation generation. And this documentation is going to be generated directly from the Dyad source code. So effectively what we're able to do is go through the Dyad source code, extract a bunch of useful information, create compelling documentation just from what's there. So it doesn't require too much in the way of sort of exposition on the part of the person creating the documentation. So we'll talk about the information that's contained in that source code and then how we bring it all together. So this is a talk that also discusses testing, and so it's worth talking about what exactly we're testing here. So our main concern is going to be with regression testing. These models that we're building in Dyad are generally hierarchical. They're composed of other models, and what that leads to is a situation where you have potentially pretty significant dependency graphs. And what that means is that then if you make a change somewhere in that rather large graph, that could percolate and make a mistake, let's say, in that rather large graph of components. It could percolate up to the top and corrupt your results. And so we want to try and detect when that's happening, and I'll talk about how we do that. And then why are we talking about testing and documentation together? Well, this covers both because testing introduces some interesting requirements on the documentation generation. So one thing is that we want to be providing cross-referencing of component models with the tests that are testing them. So doing things like, we want to be able to document things like coverage of our testing. I'm not actually going to show any of that, but I'm just saying that's an example of how it can be related. We want to be, I mentioned that we are very interested in regression testing, and so part of regression testing is having reference trajectories that we test against, so we want to be able to include that in the documentation. And I'll show examples of that. And also, anything that we're doing that's testing related, actually, when we document it, we want to kind of carve it out into a separate section, because testing is largely for the library developer and for somebody who might be interested in exploring the testing, but we really want front and center just the elements of the package that's being exported. In other words, the documentation that's central to anybody who's a consumer of the library. And so the testing, we have to organize the documentation such that the the end user documentation is sort of front and center, but the testing information is still available and accessible somewhere in the documentation for reference. And our approach, I should mention, for the testing is also declarative, just like it is with the language. And I, again, will show you an example of what I mean by that. So let's just start with a super basic model, and we'll work our way up to what we mean by testing and documentation of these things. So this is a very simple dyad model. So you have this component, which is a heat transfer problem. It has this variable T. Let's see, these are the things to note. So this is, one thing to note here is this is declarative. You might look at this and think you're looking at assignment statements, for example, but you are not. These are equations. They're relationships between the variables involved. Okay, so they're not assignments. There's no sort of procedural semantic here where we're going through and sort of assigning to registers. That's not really what we're doing. So these are just mathematical equations. There's no loops, there's no assignments, etc. There's one variable in here called T, and then what you see is that there's the variable, and then there's an initial condition here, and then there's a differential equation. Now we're going to show more complicated things, but I just wanted to start with something extremely simple. One thing that's sort of a problem with this model, and there are many problems, and I'll go through them, is that these numbers are just seemingly come out of nowhere. Like, what do these even represent, right? So we don't know what 5 and 320 and 300 even signify. And yeah, it's not obvious what this is a model of and what its limitations are. So we can simulate it though. So there's the simulation of this thing. So what this does in practice, just so you know, is it's going to take this this model. It's essentially going to, behind the scenes, it's going to build up a representation for modeling toolkit. And modeling toolkit's then going to do its symbolic manipulation on it. It's going to solve it using the equation solvers in the differential equation solvers in Julia. So we're getting all this nice performance out of Julia, but this is just a way of essentially describing the underlying mathematical problem in a sort of component-oriented way. So, okay, now I want you all to pay very close attention to that graph. I want you to memorize it. I want you to be able to tell me if a future plot actually corresponds to this result. Okay, so I'm going to have an aside here on testing. So, because that is part of the talk. So, what I'm going to do here is, I showed you that model, and before I do anything else, I am going to add testing to it. Okay, and the reason is to establish a reference trajectory for that model, because I'm going to transform that model incrementally, and I want to make sure that I'm always getting the same answer, okay, as I do that refactoring. So one thing that Dyad allows us to do is to attach metadata to the component, and so there are lots of different kinds of metadata that are involved, but for the purposes of this talk, I'm not going to talk about most of it. I'm just going to talk about one. Julia Hub reserves a sort of a segment of the metadata for our own purposes, and you can see that in this example I'm going to show. But the cardinal rule to keep in mind with metadata is that it's not a way of augmenting the mathematical description. It's not about the mathematical description. It's about things that aren't part of the mathematical description. In a sense, the data is the mathematical description. The metadata is information on top of that. So if we want to add a test case to this model, this is how we do it. So this is the same model that I'm showing you, but now you see that it has this metadata section, and this is just JSON, you know, effectively. The metadata section is just JSON. And it's, there's a schema for the data that belongs in this dyad section, but you can add your own metadata to your components, which has a lot of uses, but I'm not going to talk about in this talk. But you can see in here I've described that there should be one test case. I should run this as a simulation for 10 seconds, and that I want to actually, the reference trajectory I want to generate is going to be for the signal T. So I can run this as a test in Julia. This is just using the right square brace test functionality. So the dyad compiler that generates the Julia code also generates all the testing infrastructure for the package. And so I can just, you know, like I said, right square bracket, and test, and it'll run, and you can see the results. So there's this generates 101 tests, and they all passed. Now we'll come back to what's really going on there in a second. But there's another problem with this model, which is that it lacks any kind of descriptions, right? It's, as I said before, it's not clear what this is a model of. So one of the mechanisms that we have in the dyad language is to add doc strings. These are effectively doc strings. They might look like comments, but they're not. We can add a doc string that describes the component itself. We can add one that describes the variable. We can add one that describes the equations, the initial conditions, or the equations. So we can put them pretty much anywhere, but they always have to precede something because they are part of the grammar and they are attached semantically to the things that follow them. I could go on about why that is, but I'll save that for now. So we have these descriptions. They're treated as markdown. You might notice if you look at them that they are using various markdown syntaxes. As I said, they always apply to whatever construct immediately follows them. They're not comments. And what I mean by not comments is I can't put one like in the middle of this expression. Okay, I can't put one at the end of this line. It always has to be before, and it always has to start the line, and it always has to start with a hash. So they're just not free-form comments. And we also follow the git commit convention here of having like a single line and then a blank line and then more information. If I can remember, I'll point out why we do that. But it's basically to say we want to have a one-line summary and then a detailed piece of documentation, and we'll leverage that when we create the documentation. And obviously, we're not doing this just for the generation of documentation, which I'll show in a minute. This is immediately useful for anybody who's looking at the source code because it's telling them what's going on. But we're not done yet. There's another thing that we can do to help document these models, which is to add physical types. So you'll see here now that variable t is actually listed as a temperature, not as just a real. So why do we do this? Well, built into the Diode language are all the standard SI types, so temperature just being one of them. And these aren't just names. It's not just, okay, well, temperature's a real, big deal. Why not just say real? I mean, why not just put a comment above it, as I have, that just says temperature? What difference does this make? It makes a difference because it explicitly provides information about the units, the physical units of that quantity, and any potential limitations, right? It doesn't make sense to have a negative temperature. I mean, at least if you're talking about in degrees Kelvin. Yeah, well, I'll get to this point in a second. So this allows the compiler itself, the Diode compiler, to perform a bunch of checks. For example, it can do unit consistency checks on equations. So it can actually look at these things and say, oh, there's a unit inconsistency in here. One side has torque and the other side has force. You need to multiply by distance somewhere. It also allows you, when you're entering parameters, to check for the validity of a parameter. If somebody has an ambient temperature of -50, they don't realize that we're talking about Kelvin here and not Celsius, it can step in and go, no, something's wrong here. But it's not just about entering the data, it's also about during a simulation. If you run a simulation and the temperature, again, in Kelvin, drops below 0, something's gone horribly wrong. I mean, unless you happen to be trying to study like very, very, very cold refrigeration systems, and even then it's gone wrong. But but anyway, so the point is we can use this information in the context of the mathematical problem. So it's not just free-form text; it's meaningful in Diode. But ultimately, taking this a step further, we want to add parameters, and so. If we look at this, now this thing is actually starting to make some physical sense. We don't just have arbitrary numbers, 5, 300, and 320. What I've done here is I've gone through and I've added these parameters, descriptions of the parameters, their default values, their physical types. And what that means now is that in this model, sort of for the first time in the evolution of the models that I'm showing you, we can actually detect unit inconsistencies, right? So this one's easy, temperature should equal temperature, but when you have something like this, you actually need to have a sort of formal system of doing a very sort of mini algebra on physical types in order to verify the consistency of that. And we have an engine for doing that. So we can actually verify that the units on the left side are the same as the units on the right side. And we now have things like, because we have temperature here, people aren't going to be able to enter an ambient temperature that's -400. The tool can detect that that's an error. Okay, so things to note. Parameters allow us to add various knobs to the component model that we can turn to explore designs. Each parameter can have its own documentation, as you can see here. You absolutely should use physical types not just because it'll make it clearer to the next person that that your area is in meters and not in square inches or something like that, or is in square meters and not in square inches, but also because we can do this unit consistency checking. Okay, so we've gone from the model on the right here, which is where we started, to this model on the left. Now the question is, did we do all that right? Did we do that transformation right? I mean, I've split out all these numbers into various physical quantities so that we can specifically say what happens if the area gets larger, what happens if the mass gets larger, what happens if the ambient temperature changes. But did we get all of that right? Okay, and ultimately what that boils down to is, do I get the same answer out of both of these models? And there's a plot. So now you guys were paying attention, right, earlier when I showed that result? So can you tell me, like, did we get the same result? And of course you can't, right? I mean, you can't really eyeball these things, is the point, right? Maybe. So, I mean, it kind of looks like it, but that's, at least for me personally, that's not good enough as a testing mechanism. So if only there were a way for us to check for sure, right? And so the thing is, remember we had that test annotation, and that was the reason I put that test annotation in there, is because I sort of froze in time the reference trajectory for that model. This is all taken care of by the testing framework. It will generate the reference trajectories. You can check them into Git so that everybody else who checks out the package can run these things. You can update them if it turns out you actually had a bug in your code and you need to update the reference trajectories. But anyway, it turns out this is pretty useful because we can ask ourselves, did we get the same answer? By running the tests. We do right angle bracket test and we get this. 2 passed and 99 failed. So I'm going to say, no, we didn't get the same answer. But I might want to see this. I mean, this is just telling me there's something wrong, right? But then the question is, okay, is it possible to know where the problem is, right? So if we don't get the same answer, what do we do with that, right? We want to know where the differences are and how big the differences are and so on. So when we first ran our tests, as I said before, we stored a baseline result, and this gets tucked away in the package. And it's not just, as I said just a moment ago, it's not just about knowing that it's not the same, right? That we save this baseline trajectory so that we can actually visualize it, and we can compare our current results with the previous results. And so we can look at something like this, right? And so this is a little more useful because we can see that, like, hey, it starts at the same point, right? But we can actually see, I mean, if you look at this sort of with an engineer's eye, like, okay, the time constant here is a little bit off, right? So that helps us to sort of narrow down, like, what did we do? What did we change? What was the nature of the change we made that broke these things? And so we can actually, the fix is that we had this parameter wrong. I had 1.2 in there, and I should have had 1.4, right? So I've traced that down. And now, when I run my tests, hooray, all my tests pass, right? So this is the value of and all of this, I should point out, is accomplished by just having that one little test annotation in there. I don't have to write any code to do this. It's going to all be taken care of. I don't have to do anything, I mean, like, I go from that one annotation to just, write square brace test capability, and that's it. So now we get, our nice, agreement in the plot. Okay, so let's get back to, we went a little bit on an aside there about the testing, but let's get back to the actual generation of the documentation. So just remember, this is the model we're talking about here. This is the heat transfer model. And we've gone to some trouble to document it, to just put descriptions of things in there. Ultimately, as I said, this compiles to Julia. And one of the things that it does is it generates, the diode compiler generates various Julia functions. In this case, it will generate a Julia function for this component, which is going to be a sort of a modeling toolkit or MTK compatible component. And that means it's going to be a Julia function. So how does this help us? Well, the first place that it helps us is actually in the Julia REPL. When you load this package and you type question mark heat transfer problem, you're going to get this, okay? And the reason is because the diode compiler, when it generates the Julia code, it generates Julia doc strings that correspond to that include all of this useful information right at your fingertips in the Julia REPL, right? So including things like what are the units, what are the default values and so on, right? So this just gives you, like, okay, this is exactly how this component's should be used. So you just use the normal help prompt and it tells you sort of what the arguments are. It gives you this description. It shows you the parameter table and the variables. Okay. And you can but you can also generate essentially web documentation as well. I mean, in other words, the kind of thing you do with Documenter in Julia normally. So that helps you in the REPL, but what if you want to actually generate like a site that documents your component library? So there's two ways to do this. We have this tool called Julia Studio, which is a Visual Studio Code extension for editing dyad code. And you can go in there and there's a generate documentation command that you can run. And that will essentially, what that does is it will scaffold out a full documenter.jl directory in the docs directory. And it'll pre-populate it with a bunch of stuff, including the make script. Every time you run it, it'll update that scaffolding. And it puts in there, it essentially generates special markdown files where Documenter expects them, following Documenter conventions. So you don't have to do any of that, right? You don't have to do any of that. You just say generate documentation, and then you go into that docs directory, and you just run the make.jl. And it just does a Documenter build, and you get out your documentation, which I will show you in a minute. You can do the same thing using the dyad command line tool, so you can see it here. This isn't released yet, but it'll be released soon, so I just wanted to show how to do that. And so basically that builds your Documenter documentation for you. Now, what does this actually look like? Before I get into that, before I show you the actual Documenter site, there's basically everything I'm going to show you is derived from the source code that I showed you, completely from the source code. I didn't author any additional markdown. But there is one area where you can inject some sort of handwritten prose if you want to, which is essentially the documentation, the sort of overview documentation for the library, just to introduce what your package does. Because it can't infer that. You can figure out all those things about the components, but the actual sort of big picture part, it can't infer from that. And so there's a way that you can add essentially a README for your library. So here I've done that. I mean, this actually, it takes it from your README. If you have a README file, that's what it pulls in. So I make the README look like this, and you can see again, it's all markdown. I just add that as a README, and it'll pull that in as well. So what does it look like? It looks like this. So we'll go through a couple of the things here, but you can see this is actually an embedded iframe. So this is actually a browser right here that I'm running. Well, the whole thing's a browser, but it's a browser in a browser. So I'm actually browsing the documentation generated by Documenter. So let's go on a very quick tour here. I showed you earlier the overview stuff that comes from the README. That appears at the top. And then I can go in and I can look at, for example, I didn't show you this analysis, but this is a piece of dyad code. I'm not going to explain what it does right now, but I'm going to show you a feature, which is that these things, it's not just syntax highlighting this. There's lots of cool syntax highlighting tools out there, and we use several of them, but this is actually going beyond that, because this actually includes hyperlinks. So if I'm looking at this analysis, and I go, oh, that's an interesting thing. It's a transient analysis for 10 seconds, and it's going to run this particular model. What's in that model? This is a hyperlink, so I can click on it, and that takes me then to this documentation, which is the model that we were going through before, right? So let's walk through what the HTML documentation looks like, because it's slightly different. It turns out, I didn't show you earlier, but another piece of metadata that we have for our models is the icons, how they should appear when they're rendered in diagrams. This is a whole other topic about the graphical aspects of the dyad language, which I'm not going to get into, but just suffice it to say that they have a graphical appearance as well. And so that icon will be shown here. And then you can scroll down, you'll see basically the same thing you see in the Julia help docs, you know, a parameter table with all these types in here, the variables, the behavior. This is kind of nice. We take the underlying equations. I didn't have to write this mathematical equation. It actually goes into the component, instantiates it, and transforms what you see down here into LaTeX for a rendering here, okay, among other things. So it's not like you have to write that and deal with all the LaTeX knowledge to do it. And then you'll also see, I don't know why this doesn't, there's some issue with loading this. Let me just hit reload here if I can. For whatever reason when I do this, it doesn't always show the test results, and I don't know why. I have to hit reload. I don't know why. But anyway, it also shows the test results. So if you're looking at that component, you can say, okay, well, what does this component do? What does it look like if I actually run it? Oh, okay, that's what this looks like. So that's kind of interesting as well. And again, these are all hyperlinks you see here. So for example, if I want to understand how coefficient of heat transfer is defined, I can just click on it. We have actually a site where we keep the documentation for all of our standard libraries. It's hosted by JuliaHub, and so this is just one of those pages, but you'll see it links you right to that page, so you can just jump around following all the different types through the documentation. So, so anyway, so that I mentioned the icons, I mentioned the reference types and their hyperlinks, I showed the equations, test cases, the reference trajectory is visualized, and the current simulations results are overlaid on top of the reference trajectories. Okay, so that's that. Okay, so in conclusion, so as I just said, probably more times than I needed to, DIAD is this declarative language for composing large mathematical and engineering problems. And those definitions contain a wealth of information about you know, the models or the analyses that we can mine to generate test cases and to generate documentation. And so we extract that information to generate comprehensive documentation, and that information's, the information that's associated with the component can include additional information about what we want to test, you know, what's important for testing, and what signals are essential to the component's behavior. And then that can be used to generate the reference trajectories and the tests so that we can detect regressions as well. Okay, and all of this is to provide the best possible developer experience, right, for people who are creating these things. They want to be able to do testing with as little overhead as possible. They want to have, you know, nice readable code for end users, both in the form of documentation or if the users are looking at their source code. So anyway, that is the documentation for generation for DIAD. Okay.
Any question for the speaker?
Thanks. I have a couple of questions. The first one is, can you show the flattened code or flattened source? I don't know what it is. In the
Which code?
I think when you show
the flattened one?
Yeah.
Ah, okay. It's not going to be very interesting. I'll show you what he's referring to here. Just one second. I have to actually do like a back here to, oops, hold on. I have to reload. Sorry, I'm going to have to reload this page because the browser state is such that it's, okay. So I think what you're referring to is if you scroll down here, you'll find the source code, and then there's this little thing that says flatten source, and you have to open that up, okay? But it's not going to be any different because, so what flattening does here is, within the DIAD language, there's an inheritance mechanism where you can extend things, and sometimes it's just tedious to go back and look, to try and work your way back up through the inheritance hierarchy to find all the, you know, where something comes from. And what this is doing is it's flattening it, which means it's going to take the whole thing and flatten it out so that you can see all the entities involved in one place, which is not a good way of doing the source code from a maintenance standpoint. You want to use inheritance to avoid re-implementing the same things over and over again and promote code reuse. But when you're actually trying to understand like what the heck something comes from, a flattened view is actually kind of nice, and so that's what that's doing. But it's sort of, you have to opt in, you have to open it up to see it.
Makes sense. You want? Yeah, sure.
Well, thank you for the presentation. I think it looks really good, and it's exactly the kind of thing that we would find useful. I was curious about the reference curves that you're generating for the test. Like, how does that work out with CI? Like, do you are the reference curves stored in files that are Git committed?
Yep.
Is that? Oh,
yep.
okay.
Yeah. So maybe I should have emphasized that more earlier. Yes. So the first time you run a test, it looks to see if there's reference data. If there's no reference data, it says, oh, I guess we'll have to generate some reference data. So it generates reference data, and this is all kept in the test directory alongside the testing code. But and then then the second time you run it, it looks for a reference trajectory and it finds it. It compares it, and so then that basically locks that in. From then on, it'll work in CI because when any of your coworkers check it out, when the CI checks it out, that reference trajectory is there. But then you run into the problem that if you actually find a legit bug, then your reference trajectory is actually wrong, and you don't want to keep continuing comparing it. So there is a way to actually regenerate the reference trajectories. And then that's also part of the reason why it's integrated in the documentation. So in my experience with any kind of snapshot testing like this, the thing is sometimes, whenever you update the snapshots, you got to be very eagle-eyed about it and really take, look at it and say, is this what I expected, right? Because something can creep in. If you just go, oh yeah, add new data, stuff can get corrupted very easily. And so, because this is the gold standard, you better make sure it's right? So then being able to generate the docs. You regenerate the reference trajectories, you regenerate the docs, and then you can actually go in and say, okay, what does it look like? And then you can you could say, yeah, that's what I expected. Okay, that I'm going to keep, And then you just commit it to Git again, and then that becomes the gold standard after that. So I think John has a question, but I don't know if we have time.
Who's the next speaker that can be,
you can always ask me, John.
Yeah.
So.
Last question.
Okay, all right.
Yeah, can you talk a little bit about what kind of tests you can do? I mean, trajectories, end states, tolerance, stuff like that.
So you can do these generate reference trajectories. You can actually request. You can specify what the initial value should be and what the final value should be. That's kind of useful as well. That's about it for now. This is why, in a declarative context, of course, in an imperative context, in a procedural context, you go crazy and write a billion tests. But then you're getting into writing a programming language. So these are just the typical things. And I think regression and snapshot tests are really the best fit for this kind of a system. And I think it's pretty adequate for that. But it's limited at the moment to that. Sorry.
Thank you. Another round of applause for a speaker. And it was very good.
Yeah. If not, we can try this.
Let's try the USB-C.
Oh, I'll start with that. That's more promising.
Setting?
Let's do right for that, if that's Google Drive. Oh, okay, perfect.
Our next speaker is Cedric, and whenever you're ready, please take it away.
Do you hear me correctly? Yeah, all right. So, hi everyone. I'm Cedric. I am working with JuliaHub, but this talk will not be about anything I do with them. This is about one of my personal projects in the graphics programming realm that I feel has been somewhat underexplored in Julia. Besides all of the plotting ecosystem, there are lots of cool things we can do with graphics. And I'm going to give a talk about, thank you, about Vulkan, which is a way to interface with the GPU. It's essentially a graphics driver. So I'm going to make a small introduction to Vulkan and then to present how I made Vulkan.jl so that we can interface with it in a safe, correct, and easy way from Julia. First, I'd like to have a gauge. How many people have heard of Vulkan or have a rough idea what Vulkan might be? Okay, I guess a third, but we're not so many. So first off, I'd like to address something, is that we have in the Julia ecosystem, in the Julia GPU ecosystem, we have a lot of packages to do compute on the GPU. things that use CUDA or the equivalent from AMD or OpenCL. This is most of what you will find in the Julia GPU stack is to support this compute use case. What I want to do is actually graphics. So you can think of OpenGL or Vulkan in this case, which is about using the GPU to leverage the graphics-specific hardware functionality that makes a lot of the rendering fast. You can think of the rasterization process that you want to do when you render something on screen. Say you have a bunch of triangles, you want to do some raster operation to figure out which pixels of your image are covered by these triangles. This is something that is very, very fast with specialized hardware circuits. And you also have, for example, ray tracing that we can do with the graphics driver that can be replicated in the compute world, but usually will be so much slower. Or at least the intended use case for graphics is to target things like games or high-performance 3D applications or these kinds of things that are very, very demanding, specifically to display something. So, to quickly mention Vulkan, so it is a graphics API to interact with the GPU. I'm not saying a graphics library on purpose because it is actually just a specification, or just. It is a document that specifies what the API is, how it should behave, but there is no single Vulkan library. It's the same thing for OpenGL, and essentially it is up to every hardware vendor to implement a library, for example, a libvulkan.so, that then they will have available as part of the OS in a way that is conformant with the specification, with the behavior that is prescribed in the Vulkan specification. So OpenGL and Vulkan are two of the graphics APIs. There are others, but I notably covered these two, and in particular Vulkan, those from the Kronos group, because they are cross-platform and vendor agnostic. I mean, it will work on Windows, AMD, will work on Linux, NVIDIA, for example. And the developer should not have to care about. To zoom in? Oh. All right. Maybe I should try something to display. Oh, yeah. All right. And first, let's. It's not detecting it. Presenting here. Okay. Bit of a technical issue. So essentially it was not covering the whole screen because I have a different aspect ratio, and so I'm trying to not mirror the screen, because if I mirror it then it crops it. Mm-hmm. So I was trying to have it presented on the external screen for the presentation, but here it keeps doing it on the other. Maybe we can just, yeah, okay. I think that will be acceptable. All right. Then I just. I think you can control. Yeah, we just need it to. Okay. All right. So I don't have a replica on my laptop, but I'll just log in there. All right. So as I was mentioning, Vulkan is essentially a specification that will be then implemented by hardware vendors like NVIDIA or AMD, so that then they can ship a driver that performs what the Vulkan specification dictates in terms of API and in terms of behavior. They have conformance tests. Kronos has conformance tests to make sure that the behavior is indeed correct, and that the developer can use the API regardless of the vendor. So just to quickly mention, you might want to use OpenGL still, even though Vulkan is more recent. The reason for that is that OpenGL is easier to use because it is somewhat of a higher level API. With Vulkan, it is great because it is very, very low level API. Everything is explicit, but everything is very verbose. The driver will do exactly what you say, what you tell it to do. Whereas for OpenGL, it tries to do some guesswork to figure out, okay, what do you probably want to do on the GPU? The inconvenience for OpenGL is that if you are using it as the foundation for a renderer framework or library, then you might lack clarity over exactly what operations are happening on the GPU, what state are you in. Notably, it uses global states, which is a bit harder to reason about. But if you want to just do some graphics very quickly without diving too deep into how GPUs work and how Vulkan works, you should definitely use OpenGL. But I will be covering Vulkan, notably because I think it might be a really great foundational layer on which you can build a lot of Julia libraries that will essentially support a lot of things that you want to do on the GPU. So, as I mentioned, Vulkan is very low level, very explicit, very verbose. One disadvantage of this is that you will not want to just perform a series of calls to the Vulkan API to get your work done. What you want to have are abstractions. Notably, it takes like a lot of lines to render just a simple hello triangle, which is like more than 1,000 lines in Vulkan. In OpenGL, it would be much, much easier. In OpenGL, it would be much easier, yeah. So what you would want to have is instead having Vulkan as the low-level thing you interface with, and then build a renderer library on top of it, and then this is what your application will interface with. Application or script or anything that you like that wants to use Vulkan to render some graphics. So now let's talk about the Vulkan interface from Julia, because it might seem like ooh, lost signal again. Time I might be able to do that. Okay. And this one gets here. Okay. Do you see all of the? Do you see until the bottom? Okay, then I think I'll just stay with this if that works. All right. So when you interface with Vulkan, you interface with a shared library, a driver, which is a .so. And so it's typically a C interface, and you'll do everything thinking about C interrupt. Chronos provides a set of Vulkan C headers that you can use with clang.jl, for example, that you can parse with clang.jl to generate a bunch of functions and types on the Julia side. And this is what the Vulkan core package provides, but we're actually far from finished there. Note, for example, in the structure, this VK instance create info structure, we have quite a few fields that are pointers. And that's going to cause a lot of issues. Because in Julia, when you have a pointer, it's just like an unsigned integer. You don't have an explicit reference to the memory it points to. Which means that sometimes you may take the pointer of an object, but that object may be GC'd away because the program does not know that with this pointer you're going to access the memory of that object. And a somewhat trickier one is that sometimes the compiler will even not store things that you, will not set the memory to a value that you would initially want to set. It would just elide some stores. Here is an example of that in action, where I have a function that creates a ref, and then I take the pointer of that ref, and I just return the pointer, and then we'll try to load from it. Note that we store a 0 in the ref, so then when we do unsafe load of the pointer, we should be getting 0. But we do get some garbage value. And the reason for this is that we actually don't emit any instructions that will store 0 to that memory. If you take a look at the LLVM code, there are not so many lines, but the most important one is that we do an allocate on the ref. We don't heap allocate it via the GC. It's just going to be a temporary allocation, and we just never store 0. It's just not in there. So of course, when we try to get the int at this memory location, we get some garbage value, or the value that happened to be there. So when you interrupt with C, usually if you have to generate pointers as part of a C call, that's fine. For example, if you perform a C call and you have a ref, and your C interface expects a pointer, then Julia will call unsafe convert, like C convert, and then unsafe converts on that ref, which will turn it into a pointer, and the C call semantics will preserve the object that you pass into it during the duration of that call. But if you have to handle pointers outside of a C call, then things get a lot more dicey. And this is the case here with the structure where you have to store pointers in that structure. So the best solution that I thought of was to actually store pointers, to store the memory dependencies alongside the pointer or the structure that will contain the pointers. And this is what Vulkan.jl will emit as some kind of intermediate structure, just to guarantee correctness. It's a structure that has the ABI compatible C structure. Oh, shoot. Okay. Yes, over there. Yeah. Let's just try. If someone could prep another computer also, that could be helpful, maybe. Yeah, because it seems like the bug is in all parts. All right. Or yeah, it's enabled. It's in very small resolution and a bit weird. What if we try this? It's just not connecting. All right. Oh, okay, that's good now. All right, let's really hope that it stays. Oh, okay, so I don't have to relaunch that slide. All right, let's just proceed from there. So one of the structures that Vulkan.jl will have internally is this intermediate structure that contains the memory that has the pointers and also all the memory dependencies for each of these pointers. So that in this case, we bundle the pointer and the memory they point to, so we don't, so we make sure that the memory will still be available so long as you have the pointers and vice versa. So the way that we do it in Vulkan.jl is then we'll generate a lot of code that generates all of these intermediate structures and also higher level structures that I'll cover in a minute. And a set of functions, but all that leveraging the specification. I mentioned that Vulkan is a specification, and that's actually fantastic because they provide a specification in XML format, which we can parse and then understand what's going on. This is a small example from the specification, and I made a package called Vulkan spec that can just parse the specification and then introspect into the structs and functions it has. In particular, you'll notice that it has like almost 1,400 types and more than 600 functions. I don't want to do this by hand. Now, with this information from the specification, we can generate a few data structures. So there's the intermediate one that I mentioned on the top right. And on the bottom right, we have a higher level structure that actually contains vectors. Note, for instance, in the low level structure on the left, you have counts and pointers, which semantically are arrays, but that's the C way of saying we have an array, it's just a pointer and a size, but we can actually manipulate vectors in Julia and then have things convert automatically when we need to interrupt with C. And then we have a bunch of constructors, which take into account optional parameters because the spec says that they're optional and so on. So there are quite a few cool things we can do. Now, how do we use it in practice? Well, you can just use the Vulkan.jl package, and then you just create your structures. So here we have some application info and some instance that we create. Those are just Vulkan-specific things that we manipulate. Whereas if you actually were to interface correctly with Vulkan, without this wrapper, you would have to write all of this code. A lot of code that converts things to pointers. We have actually an array of pointers in an intermediate step that we then take the pointer to, and we need to have the proper gc.add preserve. This is a lot of manual work. Compared with what we have here, this is just, okay, Vulkan semantics. Here we have to deal just with how to interface with C in a safe way. And that's what I want to take away, or to remove, is the necessity to think about these low-level details. So I'm going to quickly show some code that does something a bit more elaborate. I'm going to go quickly on this because I don't have a lot of time. Just don't pay attention to all the details. The important is the global picture. So the first block does some initialization on the Vulkan side. Then we essentially open a command buffer on the GPU, like for the GPU, that can record a bunch of commands that we want the GPU to execute. Then we close it, and we just submit that to the device and wait until it is finished. Just note here, the only thing to observe here is that we don't deal with pointers or C interrupt at all. We just use a high-level interface. And it actually works. It doesn't crash. But if you compare it to this, you see it's like almost the same amount of code, but this one just does the first 3 lines of that one. But it does all of the C interrupt. So I would say that's a big win to remove all of these necessary steps that are just happen to be done automatically from Vulkan.jl and in a safe way. All right. I'm almost at the end. So now let's show a few example renders that you can do with Vulkan. Note that you can do essentially anything with Vulkan using Vulkan.jl. It's just that I happen to have some examples to show you. So there's the hello world triangle that takes 1,300 lines of code in Vulkan that we can easily replicate in Julia with much fewer lines of code because we don't need to do all of the C interrupt and so on. And we have a high-level interface. We have also maybe some image rendering and some blurring using a compute shader. We can also render glyphs and then multiple glyphs for different fonts, different languages. And also we can render, for example, a bunch of glyphs, but arranged in a certain way to perform a sentence, to have a sentence. This one uses a lot of styling over the text and uses style strings to do so, which greatly facilitates annotating parts of the string with specific style information. There's some image of an erosion simulation going on the left, not the final state, but some intermediate state, and then some environment rendering on the right, where we have, for example, an environment image, either as a cube map or as a query rectangular image, like a cube map being a set of 6 images for each of the faces of a cube that represents all possible directions in 3D space, and a query rectangular is a single image, but that has longitude and latitude coordinates, essentially. But really, you can do anything you want with it. There are no limits, really, and if you find limits, it's a bug. File this in Vulkan, and I will be happily fixing that for you. One small detail I want to add before we end is that, okay, you interact with Vulkan from the Julia side, but eventually, when you want to specify the shaders that your GPU will want to execute, the equivalent of kernels, but in the graphics domain, you typically, if you use Vulkan, you typically use GLSL, which is the same language as OpenGL. It's just that we compile it to a different intermediate representation, which is called SPIR-V, which is the equivalent of LLVM IR, if you will, but for Vulkan and also OpenCL. But how about we generate this from Julia? And it turns out that we can actually do so. I mean, we do so on the compute stack with the GPU compiler, so why not do that for Vulkan and SPIR-V on the graphics side? And so this is what the SPIR-V.jl package does, to be registered soon, but it's already in a pretty good state. I just need a lot more example like use cases that will surface all of the bugs that probably crawl underneath. But I've been using it for quite a while now, and it works well. This is an example of a shader that gets generated with SPIR-V, which, well, just a bunch of SPIR-V IR printed with colors. All right. So just as a quick recap, we have Vulkan, that is a specification that will dictate how your GPU should implement the graphics driver in a cross-platform and vendor-agnostic way, so that then the programmer can use it without having to care about these details. Interoperability is very tricky to get right, but hopefully, well, fortunately, we can automate most of this away with Vulkan, Vulkan.jl, leveraging the specification format that allows us to introspect into all of how the API works, how it is structured, which saves us a tremendous amount of effort and time. All right, thank you for your attention. Any questions? I can repeat the question, just say it.
Could you explain the advantage of this Julia integration with Vulkan when compared to any other integration with other packages? Like, I expect there are some other interfaces for Vulkan from other packages.
So the question is about what changes from when we interface with SPURV on the Julia side as opposed to how we do it on the other Julia GPU ecosystem. Is that it?
Integration with Vulkan.
Yes.
From other languages. So, I mean, this is
Oh, from languages that are not Julia.
integration of Vulkan in Julia, and I wonder if there's any advantage of this implementation over other integrations.
Oh, yeah, okay. So the question is about, we do this integration in Julia, there are other integrations in other languages, what are advantages of this wrapper in Julia compared to, for example, how Rust interfaces with Vulkan. The main advantage, I would say, is that we use Julia, which is a fairly high-level language. And for that, I made a lot of work to make sure that we get a wrapper that gets us also a high-level API. So I'm going to go back to my main example here. This is not something you would do in Rust. In Rust, you would allocate your variables and set a bunch of fields, and then perform a bunch of manual calls to manual IPA calls, and then check for status codes, things like that. And a lot of this is automated away here. For example, there are a few patterns that were automated that are quite low level that we don't really want to deal with in Julia. One of them, for example, is that most of the time Vulkan fills in some pointer that you give it or some ref that you give it and then returns a status code as part of an API call. Then you have to check the status code, and then to actually get the semantically returned object from the call, you would just dereference the pointer that you created just for that purpose. Well, here we can just have result types.jl, for example, to wrap a call to Vulkan. That indicates that we can unwrap or check if we have an error or not. And also we just semantically return an instance. For example here, in this manual example, we do have to construct a ref to a VK instance, then call VK create instance towards the end, and then dereference the ref. So that's just all automated away here. You call create instance, which is another high-level function provided by Vulkan, and it returns you an instance. Doesn't return you, it doesn't fill in any pointer semantically. Any other questions?
Have you explored shipping parts of Vulkan's runtime, like the ICD driver or any actual drivers as JLLs?
So the question is about have I explored any shipping of Vulkan, or the Vulkan runtime as JLLs? Yeah, I explored it with, I did actually some work to have Swift shader, which is a CPU implementation of Vulkan made by Google. So I compiled it with Binary Builder for Linux and maybe macOS, but not Windows, because there were a lot of issues. Or unless I just used the tarables and did not compile it. I don't remember exactly, but yes, I did explore that, which is very, very useful for testing, so that then you can just grab and implement a CPU implementation of Vulkan from Binary Builder as a JLL and use that in your test suite. You don't need an actual GPU to run Vulkan tests on CI. Yeah.
Any other questions from the audience? I have a small question.
Yeah.
Among all your parameters, is there anything, I mean, I assume so, but that controls the quality of the image? I assume so, or not? Yeah.
So you mentioned...
Is it like easy to change? I don't know, you want to render like a more quality image or not, or?
Yeah, so for example, if you want to change the quality of an image, you might just change the resolution, and that's just a single parameter that you have to change in your Vulkan code. That's quite easy. Now, if you want to enable a bunch of render options, like whether you want to do multi-sampling or not, and also in the shaders themselves, it's actually, from the Vulkan side, it's actually fairly easy. If you want to expose it from an application side, you have to rebuild a bunch of structures, and it might actually be a tiny bit of a challenge, but it's just something that is very explicit in Vulkan, so it's not surprising behavior, just potentially some more manual work depending on how you want to expose these parameters.
Okay. Well, let's thank the speaker again, even with all the technical issues. Thank you very much, and round of applause. And we break for lunch.
Thank you.
We come back at 1:30, and yeah, enjoy your meal.
Thank you again.
probably easiest to use HDMI directly. Does that work? Or is the beamer not on yet? Okay.
No audio.
Sorry?
You don't have any audio?
No. Just a mic. Just a mic. Just want to make sure it doesn't disconnect like the previous speaker. I think there was a dongle issue or maybe a port to his laptop.
Maybe, because I think it was good after we switched.
Switch it on anyway. Yeah.
There wasn't another switch.
This looks to be. Yeah, that works.
When you're ready,
Yeah. In front of the mic. Yeah, sure.
Hello, everybody. While Tim gets set up, just want to say thanks, everyone, for coming to the GPU Mini. We're going to have several exciting talks today and then end on a panel discussion. So, oh my goodness, okay, I'm hearing my own voice. Please stick around for that and take it away, Tim, Julia Hub, GPU Impresario.
Thank you. Thanks for attending. So today I'm going to be talking about OpenCL.jl, which is a new GPU backend that I've been working on for the past year, and how we revived that to run GPU code on the CPU. So a bunch to unpack. Before that, I'll start with some motivation for this whole effort. And the motivation for this work starts with kernel abstractions, which I'm assuming many of you will be familiar with. So kernel abstractions, you can see on the left-hand side, there's a bit of code that uses CUDA.jl to allocate some data and launch a very simple vector addition kernel. On the right-hand side, you have the equivalent using kernel abstractions, and you can see that only the kernel definition and the kernel launched have been substituted with something that's vendor neutral. And we do that by using macros. And using these macros, we can target a bunch of GPU backends. And that's fairly straightforward because all GPU backends, whether you're using them from Julia or from the vendor-specific languages, they use a SPMD abstraction for kernels. SPMD is single program multiple data, as opposed to SIMD or MIMD. It basically means that you write a single piece of code that's going to be executed across a whole bunch of data. And the code differentiates what it executes by using certain intrinsics, like here, the @index intrinsics we define in kernel abstractions to figure out which work item this instantiation of the thread has to work on. And all of our GPU backends take this kind of kernel language as input, which means that the conversion from the kernel abstractions definition to the vendor-specific one is very straightforward. For the CPU, that's not the case, because GPU kernels often are launched over tens of thousands of threads, so we cannot simply use one CPU thread for every GPU thread, meaning we have to do parallel code generation. And for example, for a simple reversal kernel, which will reverse the elements of an array, that basically boils down to generating loop nests, processing multiple work items of each block in a row, and then in between the loop nests, you have implicit synchronization because the one loop net finishes and then the other loop net starts again. So that may seem like a fairly straightforward mapping. The problem is that SPMD kernels do not cleanly map onto loop nests. And as a result, we have quite some issues with this mapping. One, for example, is the issue of scope. Things that are defined within the for loop that we generate are not visible outside of the for loop. So that's a clear violation to what the kernel was originally written as. You might wonder at this point, why do we even have a CPU backend at all? Because kernel abstractions is a GPU programming abstraction library. And it is, that's true, but originally we added a CPU backend to facilitate debugging so that you can at least run the GPU code on the CPU, add some print statements, and so on. Nowadays, now that kernel abstraction is becoming a little more popular and more Julia libraries are being written using kernel abstractions, the CPU backend is also becoming more important in order to ship code to people that do not have a GPU, because you cannot assume that everybody has a GPU in their laptop. One example of that is, of course, continuous integration services. It's fairly hard to get a CI service that has a GPU. So if you want to test your library, it's good that we support a CPU backend at least. And finally, it would also be great if we could use the CPU backend to extract some more performance from your system, because ultimately it's silly if those powerful CPUs aren't doing nothing while you have the GPUs computing. So basically, that's just a bunch of motivation why it is interesting to have a CPU backend. But as I explained before, the whole mapping from these SPMD kernels to parallel CPU code that uses for loops is tricky at best. And it also has some implications on the kernel abstractions API. For example, to get by the scoping issue I mentioned, kernel abstractions has this @uniform macro, which tells the system that a certain abstraction, a certain expression can be hoisted out of the for loop and its side effects can be visible for the entire work group. The counterpart of that is the add_private macro, which makes sure that something is only visible for the current work item. In principle, this shouldn't be necessary because the SPMD kernel is fine by itself. It's only the mapping to for loops that complicates and introduces this whole scoping issue. And there's a bunch of other issues. For example, it does not support early returning from an arbitrary point in the kernel. It limits the how you have to use the kernel abstraction's primitive functions, which has to be in an add kernel function. It also requires the synchronization to happen at top level, and so on and so forth. So the bottom line here is that the CPU backend has quite some issues, and those issues aren't limited to the CPU backend itself, but they also have an impact on the kernel abstractions API as a whole. So the conclusion basically here is that we need a new CPU backend that works, and as a result, hopefully can unleash the kernel abstractions API. And that's when we discovered POCL. POCL is a portable open computing language, which basically is an implementation of OpenCL. So OpenCL is an API that's being used to execute compute programs on the GPU, but it's just the API. You have a driver implementing this API, and POCL is one of these drivers. And as you can see at the bottom, POCL supports a whole bunch of backends, and one of those backends is a CPU backend, meaning they do all of the complicated mapping and compilation of SPMD inputs to parallel loops in order to execute it on the CPU, so we can piggyback on them. Especially so because it's OpenCL, and we already have OpenCL.jl. And with OpenCL, you can feed SPIR-V kernels into the system, and we have GPU compiler to compile Julia code to SPIR-V. So in principle, we can simply use OpenCL. Sadly, things aren't that nice. OpenCL.jl, turns out, was pretty old and unmaintained. You can see the contributor chart on the right. It was one of the earliest packages that existed in Julia, earliest GPU programming packages, but nowadays it was desperately in need of a maintainer. So that's what I've been working on for a handful of months, the past couple of years, reviving OpenCL.jl such that we can use it to target the CPU backend of POCL and unleash kernel abstractions. So as I mentioned, OpenCL was one of the first GPU programming packages that we had in Julia, which as a result also influences how you program a GPU with it. So here on the left-hand side, again, I'm rolling with vector addition as a very simple, understandable example. You can see how, first of all, the kernel code has to be written in OpenCL-C. So back at that time, there wasn't GPU compiler, so there wasn't a way to compile Julia code for GPUs, so you had to write your kernels in C. We then allocate some data on the CPU, but before uploading it to the GPU, you had to manually manage your state. That is, which device to execute on, a compute context, a command queue. You had to instantiate all of that manually. After that, you had to use lower level APIs to compile your kernel, and finally upload the data to the GPU using a buffer, which is not an array, so no full-fledged array abstraction, and then finally launch the kernel with slightly clunky syntax. So this is very different from what our modern GPU backends look, and as a result, integrating the current state of OpenCL.jl into code that assumes the GPU backend, such as the other GPU backends, is not going to work well. So OpenCL.jl integrates fairly badly with the rest of the GPU ecosystem. So first of all, we modernized the package by, for example, getting rid of the explicit global state, switching to an array abstraction. So now we have the CL array abstraction instead of CL.buffer, and switching to a much more C call-like calling function CL call instead of punning on the getIndex function on a kernel object. So that was the first step, modernizing the APIs, making sure you don't have to use low-level stuff. And next up, we integrated with GPU compiler in order to support compiling Julia code straight up to SPIR-V code, which we can then feed to the driver. And now this is the current state of OpenCL.jl, which is extremely similar to all of our other backends. You define a kernel function just as any ordinary Julia function, and you launch it using a macro here at OpenCL, which is very similar to at CUDA. So OpenCL.jl now already is a very potent GPU backend you can use. Behind the scenes, that required a significant amount of work. So there was obviously the integration with GPU compiler in order to generate SPIR-V code. The array abstraction implements the entire GPU arrays interface, so we can reuse all of that functionality that we already have implemented in GPU arrays. We obviously provide a kernel abstractions backend. In order for this code to compile, we also had to support more modern versions of OpenCL, as well as detect which extensions your driver supports in order to be able to derive a pointer, because generally in OpenCL you work with opaque buffers and handles to it, not with device pointers, which is tricky because an array in Julia is a struct containing a pointer. So having to work with that required exploring and detecting which extensions your device supports and accurately selecting one or another. And finally, we also use JLLs to package up as much of the OpenCL ecosystem as we can, namely the loader, because again, OpenCL is plugin driven with a bunch of drivers that can registrate, and the drivers itself being Poggle. And as an example of that, here I'm showing how on the current version of OpenCL, you can import the package, OpenCL, you can import a driver, Poggle, for example, and then when you perform the first API call, the OpenCL ICD loader will detect all available drivers, both drivers that are activated through a JLL, which will register themselves automatically with the driver loader, as well as any system drivers available on your system. For example, here, this is on my workstation. I run OpenCL.version.info, and it obviously reports the Poggle driver, which has been imported through a JLL, but also my system drivers, such as the Intel one and the NVIDIA one. The next step is taking all of that functionality and integrating that in kernel abstractions. And this is still a work in progress, so it's not released yet, but in the next version of kernel abstractions, you will be able to use the Poggle backend, which will be an integrated backend, and you will be able to take any kernel abstractions kernel function and execute that on the CPU using the Poggle backend. It's a very lightweight way of doing things. We don't actually depend on the entirety of OpenCL.jl. We just integrated whatever we needed, as well as Poggle, into kernel abstractions. Yet we now support the entirety of kernel abstractions. So because of relying on Poggle's SPIMD to CPU compiler, we don't have to do the manual mapping of kernels to for loops anymore. It also directly uses Julia arrays, so it's very convenient. You don't have to use a separate array type. There is one disadvantage, namely that because we now go through GPU compiler, the kernel code is now also having to stick by the subset of Julia that GPU compiler uses. So you cannot do dynamic invocations anymore, you cannot trigger the garbage collector anymore. This was something that was possible with the old CPU backend. The new CPU backend has to stick by the rules of the other GPU backends. But to some extent, that's a good thing, because you can develop code, you can test it on CI, and if it works on CI, you know that it will work on the other GPU backends as well. So disadvantage, that may be an advantage as well. So that was how we can use Poggle through OpenCL to enable a CPU backend and kernel abstractions. But OpenCL.jl itself can do quite a bit more for us. So again, the current state of affairs out of the box is that you can use OpenCL.jl to, for example, program your Intel GPU, because the Intel GPU supports SPIR-V. You can also use it with NVIDIA GPUs, but I use the dotted line because the NVIDIA OpenCL driver does not support SPIR-V. So you'll have to use kernels written in OpenCL-C, and if you're using the NVIDIA GPU through OpenCL, you will not be able to compile Julia code to OpenCL code for your NVIDIA GPU. That doesn't really matter because we of course have CUDA.jl, which should be the preferred package to work with NVIDIA GPUs. But it is possible to use an NVIDIA GPU through OpenCL.jl. Then there's of course also Pockle, which has a CPU backend. But if you remember the initial overview I showed of the Pockle architecture, it also supported a bunch of other backends. So we can actually use the NVIDIA GPU through Pockle, and that does support SPIR-V to OpenCL compilation. So through Pockle, it's not part of the released JLL yet, but if anybody would be interested in it, it's actually possible to use the NVIDIA GPU and a bunch of other GPUs through OpenCL.jl by using Pockle. We're also investigating some other possible routes of using backends such as NVIDIA's, which only supports OpenCL-C, and that is by using the SPIR-V2CL binary. SPIR-V2CL is a project that aims to cross-compile SPIR-V code back to OpenCL-C. And again, for the NVIDIA driver, that's not particularly relevant, but this may be relevant for embedded GPUs, because there's many embedded devices which have an OpenCL driver, but that OpenCL driver only supports OpenCL input. So with this, it may be possible to extend the reach of the Julia GPU ecosystem to all of these embedded devices that support OpenCL. There's other interesting drivers. For example, there's Rustical. Rustical is an OpenCL implementation that's open source and is part of the Mesa open source graphics library. Rustical is an OpenCL driver and it runs on Gallium drivers. Gallium drivers are the drivers that are internal to the Mesa project. And one of those drivers is Zinc. Zinc is an interesting driver because it cross-compiles SPIR-V to Vulkan. So with this unholy setup, we can actually compile Julia code to SPIR-V and then cross-compile it via Rustical and Zinc to any Vulkan API that supports SPIR-V compute shaders. Again, this makes it possible to run on an NVIDIA GPU via yet another way. But for example, it also makes it possible to run on Raspberry Pis, because the Raspberry Pi 4 and 5, they actually come with a Broadcom GPU Vulkan driver. So with that driver and this cross-compilation setup, it is possible to run code on a Raspberry Pi. So let's demonstrate that in detail. I've built Rustical and created the JLL already, so you can actually import OpenCL, import Rustical, and if you then do version info, you can see on my workstation that the NVIDIA GPU is listed twice. Once via the NVIDIA driver, which is a proprietary one, but that only supports OpenCL-C. It's also possible to use it through Vulkan by using Rustical and Zinc, and that now does support native compilation. And you can show that, I can show that by the final expression, which does broadcast operation, which obviously is implemented natively in Julia, and here is being cross-compiled to a format that can run on the NVIDIA GPU. And the other example was using a Broadcom driver. This is on a Raspberry Pi 5, again, allowing us to compile Julia code for the Broadcom GPU in a Raspberry Pi 5. And basically, the only thing this requires is a sufficiently powerful Vulkan driver, because it needs a handful of extensions, such as, again, the buffer device extension that allows the system to take device pointers, which is something we require to be able to represent all of Julia's structures on the GPU. And if you're interested in how this works, you can actually set an environment variable, the Zinc debug environment variable. Here I'm setting it to NIR and SPIR-V, which will show the intermediate NIR code, which is the new IR, as well as the output SPIR-V code. So first I'm showing the SPIR-V code that we generate using GPU compiler, and you can see here that the op capability is kernel, which means it is a compute kernel SPIR-V binary. Then it's going to get compiled from, translated from SPIR-V into Mesa's IR, and then finally Vulkan shader, Vulkan compute shaders come out of it and can get passed to the Vulkan API. And this all happens automatically by Rustical, because Rustical is a full OpenCL implementation, so we don't actually have to use Vulkan.jl. This automatically goes through OpenCL. I'm mentioning here help wanted because the idea here is that these are proof of concepts. It does work, but it needs to be polished. So if anybody's interested in running Julia on any of these devices using these flows, the hard work has been done, the proof of concept is there, the JLL builds. Now we just need somebody to go through and fix all of the paper cuts and all of the small issues that are left to get the system to pass all of the tests. But for example, in the case of the Raspberry Pi, there's quite a bit of test failures. In the case of NVIDIA, almost all tests pass. So if you're interested in running OpenCL on an NVIDIA GPU, this is the way forward. The other way forward was to use SPIR-V to CLC, which is the source-to-source compiler going from SPIR-V IR back to OpenCLC. You can here see the generated kernel for, again, a simple vector addition. Again, proof of concept, works for the simple stuff, does not work for the complicated stuff. So if you're interested in targeting specific embedded devices that only support OpenCLC, the basics are out here, get in touch, and we should make it possible to extend the Julia GPU toolchain to way more devices using this. All right, a little faster than expected, but nonetheless, that was it for my talk. So as a short summary, we've brought OpenCL.jl back from the dead. It's modernized and fully integrated with the whole GPU ecosystem now, allowing you to use it to program OpenCL GPUs in a modern way that integrates well with the rest of the Julia ecosystem. This allows it to target quite some new GPUs that weren't possible to program before because OpenCL is a fairly versatile toolkit, but ultimately the goal for us is to use this in combination with POCL and take the kernel abstractions library to a next level by adding a proper CPU backend to it. Thanks.
Cool. We definitely have time for some questions. Just please put your hand up and wait for me to give you the microphone so that the question will appear on stream. If anybody has questions for the speaker. Awesome.
Awesome work, Tim. Perf questions. I know it's early times yet, but you have data on, for instance, CUDA, or rather NVIDIA backend performance through OpenCL versus through CUDA, and natively written Julia with add threads or whatever versus an OpenCL kernel on the CPU. Do you have like any comparisons?
At this point in time, we don't have any proper performance results to show. I haven't even tested them when trying to do the funky cross-compilation to, say, an NVIDIA GPU or a Raspberry Pi GPU. We have done some tests on the CPU, and it is, in certain cases, able to outperform even native threaded code on the CPU, because it also does auto-vectorization within the for loops that it generates. The only problem there is that we're actively working together with the POCL team to make sure that Julia code is compiled correctly. So currently the parallel region detection code that they have is not always properly able to deal with the code that Julia generates, specifically because of our heavy use of exceptions. That means you get aborts and unreachable code in heavy divergent parts of your parallel regions. And the auto-parallelizing compilers really do not like that. So we're still trying to figure out a way there, what the best way is to support the parallelizing compiler, which has great performance, and to support it widely with Julia code. So once that's done, we can move on the next step and do some performance evaluation.
So we definitely have time for a couple more questions, so don't be shy.
I missed the start, so hopefully you didn't answer this already. But with the existing kernel abstraction CPU backend, you don't have to install anything. Like, you can just run it and test it. But with this new backend, you will be required to add a new package to actually use it, correct?
No, because we opted to not have it depend on OpenCL.jl itself. So we chose to pick the API wrappers and the JLLs that we need from OpenCL and add them as a default dependency to kernel abstractions. So when you'll install kernel abstractions, you'll see that it will additionally pull the POCL JLL, but it will be a full dependency of kernel abstractions. So you will not have to install any additional dependencies. It will still work out of the box. And in order to do that and not have people pay the price of having to precompile the whole OpenCL stack, we moved that code inside of kernel abstractions.
Okay, thanks.
Do we have any other questions for the speaker? Is that a question over there? Or, okay, someone was just stretching. We'll give people a second to think. It's hot in here, so. If not, let's thank Tim again for the great talk about OpenScale. And we'll come back at 2 p.m., so if you need to run to the washroom, Aaron, if you want to start setting up, Aaron's going to be our next speaker talking about trajectory bundles.
I have an HDMI. Do we have the USB-C adapter? I can take this. Somewhere?
Yes.
Okay, cool. I
Yep.
might need it later. So. I love your shirt. Is that mouse? Oh my god.
Yeah.
I think it's great. This is a little from there, so they like went crazy at the Minneapolis Arts meeting and like had all their first results.
Looks good.
When you're ready.
Perfect.
This is just a yellow background.
Oh, okay.
Yeah.
I wasn't sure.
No, it was on yesterday.
Okay.
And it was even more yellow. But now I matched the yellowness of it to match. Yeah. All right. Whew. Yeah, I should have precompiled this package before. Oh yeah. It's still in precompilation. To hell. It just keeps recompiling. But yeah. So it's not gonna be live, but there's gonna be footage. Okay. He's gonna use the readme.
Yeah, drop in some screenshots, show some stuff, answer questions.
Yeah.
Yeah.
Yeah, exactly. I mean, it's still recompiling. It's been going like since like noon. There are some, I had to update things, there were things, something was, yeah. And I tried, then I realized, oh, I can't even run on my laptop because it's a bunch of precompilations. That's self-recompiling too because of the M4 chip of my old laptop. Yeah, this is all very experimental. I don't know. I doubt it. Yeah, it was the exact same thing that's already saved somewhere, so it should work. I think it has to precompile every single ordinary DiffyQ integrator method, which is a terrible fucking thing.
All right, so it's 2 p.m., so we can get started with the next talk about trajectory bundles.jl. So take it away.
Yeah, hello everyone. It's a pleasure to be inside of this building for the first time, actually. It's been 3 years living in Pittsburgh, and I've never stepped foot in here, but it's super cool. And it feels like it's time to go over a little bit of history, which is what I plan on doing to start this. So back in the 80s, across the valley here, Carnegie Mellon was doing some of the pioneering work in robotics at the Leg Laboratory with Mark Rabert, who since went on to move to MIT and then found Boston Dynamics. So the Leg Lab was doing really kind of crazy for the time and crazy now, just look at hopping robots. So these are robots that are doing basically control. There's a computer connected to them offline, and they're doing these kind of like dynamic hopping things with like actual like modern kind of what we think of as modern kind of control algorithms. So if I skip ahead and I show like, so there's this hopping robot, there's a lot of bunch of other like four-legged hopping. So the control methods were improving and we could control more hardware. At the same time the control methods were improving, they were taking advantage of advancements in computing. So, come on. Okay, so the same kind of computing and control advancements also allowed CMU to like do some of the first self-driving cars and win the DARPA Urban Challenge. So basically starting the self-driving car craze. And this was back in 2007, so quite a while away, or quite a long time ago, and we still haven't really solved self-driving. But computing has gotten a lot better, and those edge cases are being taken care of. So fast forward to today, and my lab is also leveraging computing and control algorithms to do a lot of cool things. We are doing game theoretic self-driving, dancing robots, tiny robots that are doing online control, drones, expanding space structures, like all kinds of quadruped stuff, lots of different fancy things, even swimming robots, and even what I work on is quantum control. So I control quantum computers, which is going to kind of become evident shortly. So what do we really do to do these kinds of things? We do something called trajectory optimization, where we have some physical model of the world, of our robots, our satellites, and we're trying to get them to do something specific. So we can encode that as a cost or a constraint, and we say like, don't violate the laws of physics, like don't run into each other, don't run out of fuel, like don't spin too fast or don't drive too fast and kill the human. So there's all kinds of constraints you want to put on these optimization problems, and let a computer solve these and get like really good solutions and do this like fast and online. So this can be abstractly written down in this formulation. So there's a lot of stuff going on here. You have like basically though an objective term. So you're trying to minimize some objective that's encoding like what you want to do, where you want to get to. You have your dynamic, so you can say, okay, my state at some time step in the future is a function of my current state and the controls at that time step. And then you can put all kinds of constraints on, and you say, okay, we're going to start at some initial point, and let's try to get as close as possible to some final state. And then we're going to optimize over all the states, all the controls, or in some cases you might just optimize over the controls. So like typically our model of the world is of the form of an ODE. So we have some dynamics. And we say, okay, we're given some controls, let's evolve our system and see how close we get to some like end goal. So that's great. We can see, oh wow, we missed a bunch. We can take a gradient, and then we can take a step, and we can on the control space, and then we can roll it out again and see how we did. So we can see, okay, we got a little closer, take another gradient, and see if we can get closer. And this kind of works pretty well, and it works enough. But it's really kind of not taking advantage of what the computers actually can do. So I'm not a GPU programmer. My ideas of GPU is from basically the Mythbusters. So like they have this demo where they kind of show this robot doing a serial type computation. I don't know if anyone's seen this video. But like this is not optimal. Like ideally we could do a lot better. We can do things in parallel. Okay. Oops, sorry. Okay, so let's say like now let's do stuff in parallel. Let's sample a bunch of controls from some distribution, some around our current control and with some variation, and we can say, okay, let's run all of these at once.
And then we can say, let's pick the best one or some weighted sum of the best ones. And this is actually something pretty cool. This is model predictive path integral control. So this is MPPI, and this is done. There's a lot of cool GPU work for doing these types of, solving these types of problems in parallel, leveraging the parallelization of a computer. And so like one thing that you'll notice is like starting from some initial state, a lot of these ODEs have like chaotic-esque behavior. So as you go a long time horizon, your errors accumulates. So as you might start somewhere close, and then by the end, like, can you really trust your solution giving a solver? And it's hard to say. So like there's a lot of work in ODE solutions and doing ODE stuff to do really high solution quality for ODEs, and then maybe run those in parallel. And that's a really good idea, and we like that. But you're still never going to like fully get rid of all this error. You might be wondering, like, how do we actually parameterize these trajectories? And what we do in practice a lot of the times is like you discretize space, and then you say, okay, we're going to put some splines. We're going to find the position of the controls and the direction of the controls at each time. And this graph is kind of in state space, but ignore it. We're basically doing some sort of spline-based control, and then you can sample your controls around these splines. So back to this video, which I love, is like they build this thing and they say, well, like obviously we want to just do as much in parallel as possible. So like instead of doing some serial computation, like do something in parallel and make something beautiful all at once, which is potentially possible. So we kind of, in our lab, we've been looking at this and saying like, yes, why can't we do more in parallel? Like why can't we divide up the time and maybe stack a bunch of these ODEs and do things more disjointly? So like let's say instead of sampling just controls, we sample states at each of these time steps. And we start with some initial point and we involve some of these forward. And we call this like a bundle. And then we start from another xk and we evolve around there and we evolve forward. And like we're going to call these things kind of like the bundles. So this is like the x bundle. You sample around some current xk, and then you evolve these each out. And what's cool is these error regions are much smaller because you're integrating over a much smaller time horizon. So like we can keep doing this, and then we call this the function evaluation bundle, so the rollout bundle. So this is the dynamics at the end, and like we match this up with some bx k plus 1. So like we have these bundles that kind of are moving around, and then what's kind of cool is you can do all of these in parallel. So you can really stack your parallelization together. There's a problem, which is like what does it mean? Like we kind of want these trajectories to link up and not be totally arbitrary. So like in some sense, we kind of want like the function evaluation bundle to kind of equal the state bundle at the next time step. So like we really want to kind of stitch these things together in some way. So this is kind of leveraging some of what they did with MPPI. But kind of doing it in a new kind of formulation. So I'm going to talk a little bit briefly about convex combinations. So we have this little picture of our X bundle kind of evolve forward, and then we have the next X bundle. And like let's say like these evaluations, these function evaluations are approximately affine. So you can say like the function evolved on a weighted sum of input states. Approximately equals the sum of the weighted sum of the output states evolved for each one. So like this is maybe a good assumption in a lot of cases. In control, this actually is a pretty good assumption, and then we have some work kind of proving some theorems about this for certain cases of dynamics. And then crucially here, this is a convex combination. So these alphas are greater than 0 and sum to 1. So it's kind of like a weighted probability. So like you can imagine if you have 3 points, your convex combination is going to live somewhere in between them. So this P point is a possible convex combination, but this Q point is not. And then like, so what we can do is we can say, all right, so we're going to enforce a constraint that says like the convex combination of these Fs equals another convex combination of the x's at the next time step. So you have these alpha weights, these convex combination weights, kind of enforcing your dynamics between time steps. So this is one of the crucial equations of this. And then like going back and looking at this problem, I wrote this in a very specific way. So in here we have these residual functions and the kind of norm squared. So what you can do is you can say, okay, let's apply this residual function to each bundle, each column of the X bundle. So you kind of evaluate the X bundle here. And like you can plug in like the same kind of alphas here and you get this problem. So I'm going to walk through this slowly. So this is crucially an optimization problem. While this was an optimization problem over all of the X's and all of the P's, the controls, the spline parameters, this is an optimization problem over only the alphas. So we did a bunch of rollouts to get these bundles, and then we're going to solve an optimization problem where we say like, we kind of have this residual, these objective bundles. We have these X bundles weighted, and like basically this is kind of matching up the weighted sums of all these alphas. Kind of have to, we're going to minimize the cost and then make sure that the dynamics are satisfied also. And crucially, this is a convex quadratic program, which is really nice because there's a lot of really awesome tools for solving convex problems and solving them efficiently and at a really large scale with a lot of variables. So just to highlight some more of these things, we have a constraint bundle. You have your X bundle equals X in it. You have your kind of simplex constraints for your alphas to be normalized or sum to 1. And this can all be really easily encoded via convex.jl, which is what we actually use. So just to kind of rehash exactly what we're doing, we want to use GPUs. So we're going to use diffieq GPU.jl, which is a really nice package for doing parallel ODE solves when you're just kind of changing the parameters. So, and then like this kind of gives us our bundles, and then we can take those bundles and solve a quadratic program using convex.jl and Clarabelle over these alphas and with some constraints, and it's a pretty simple program. We get back these alphas, and then we can update our states with these new weighted, the bundle times the alpha gives us a new xk, which is the next iterate. So we're basically doing kind of sequential quadratic program, but really leveraging parallelism and GPUs and convex programming, which there is a Clarabelle GPU, which we haven't implemented yet, but it seems like a really cool direction to go in next. Okay, so now I'm going to peek over here and see if things precompiled, and it doesn't look like they did. Okay. So this code is very experimental. It does work. So in some sense, this package did work. So this is trajectorybundles.jl. It's on GitHub. When I last touched it 4 months ago, it was working. So I'm going to walk through basically a kind of a simple bilinear optimal control problem. So this is a problem that's very common in robotics when you have like a satellite, which is you're doing some rotation on like a satellite or a drone, and you're trying to like get it to rotate into some position. So this can be thought of as a quaternion. It can be thought of as SO3. It can be thought of as SU2 actually. So it's the same problem as controlling a qubit actually in quantum control, which is why I chose this. So it's pretty simple to load up the package. You just use linear algebra, sparse arrays. You might not be required to do these. There's this really nice package named trajectories, which we wrote to do trajectory data handling, and it kind of handles all the indexing and stuff underneath. And then there's this package trajectory bundles, and of course CUDA. So this does work on GPUs, at least it did. So like we can define some generators. We define some abstract matrices that are basically the X rotations, the Y rotations, and the Z rotations. We say, okay, we're going to call GZ our drift, and then our drive, we can control X and Y rotations, and we're kind of spinning around the Z axis with some frequency. And then we also spinning around, we have some like kind of modulated nonlinear controls. And what's cool about this is like, I didn't highlight this earlier, but like nowhere in this method is derivatives ever come in. So your dynamics can be fully, like, doesn't have to be differentiable at all. You can just do whatever you want to do in your dynamics. They just have to be able to be simulatable forward. So like this, we had a bunch of time dependence, which depending on how fast these frequencies are, it might be really hard to diff through, and the properties of those gradients might not be so great. So anyway, we're summing these up with our controls. So our controls are these U's. And we're just kind of weighting each control. And then we say our dynamics is basically this G matrix multiplied by the state. So bilinear control, a la this kind of formulation here. And this is a really simple problem and has some nice properties because it's linear in X, it's linear in the state. This is a kind of a little function I wrote to actually kind of build a matrix multiplication kind of kernel to actually run on the GPU with diffie-q GPU, because you can't do matrix multiplies directly inside of here for some reason. And then we say, okay, we started in basically the down, we started down and we want to end like up. And then we're going to say, okay, we're going to have 100 different time steps. We're going to have a time step of 0.5, and this is just some parameters you have to include. You say, okay, we want our controls to be within some bound. We're going to do some random initial guess. We're going to roll this out, and we're going to build this name trajectory. So like you can kind of see here, we just kind of have to throw in an initial trajectory for the x's, an initial trajectory for the u's as a matrix. We just say, okay, the u is our controls, the time step is delta t. You can show bounds, initial, final, goal, all kinds of stuff in this name trajectory, and then you can just pretty simply plot it. So you can see the dynamics are like pretty oscillatory. Our controls are totally randomized, and so this seems like it could be a hard problem, but let's see what happens. So we include some weights on the objective. We say we want to weight the goal by this and regularize the controls by this. And then this is how you're going to define losses at the moment. You kind of define a function that says the state variable goes to x minus the goal. And then the u's, so these were in line with this formulation where you have a final cost and you have a residual at each time step. So we're basically matching that exact form. Same with the controls, same with the initial, and you just define these all as functions. You create these residuals and constraints. Define how many samples you want to take. So this is a crucial kind of parameter, and we kind of just set it equal to basically order the dimension of the state. And then you can set up this trajectory bundle problem. And then pretty simply like define like there's different like kind of sigma schedulers. So I didn't get to highlight that, but basically how wide your bundles are sampled away from your current state is kind of like scheduled in some sense, and there's a lot to do in this regime. And then you can solve this, and you can use a CUDA backend, and then you can plot. You can see we found this solution, which is kind of interestingly kind of tracking the frequencies of this signal, and this is a pretty interesting control signal that came out to track this time-dependent control. And you can see over here, basically the log loss of the objective value over time, and like we kind of reach some converge point, and then we terminate the algorithm. So yeah, so that's in a nutshell kind of how this algorithm works. I'm going to say like there's a lot of room for improvement in here, as we can see, as there's like specific structure in a lot of these dynamics problems. Doing stuff with diffie-q GPU I think could be optimized in a bunch of ways. We haven't included like kind of the freedom to choose different times, but there's a way to do that. Doing stuff on the GPU, and then maybe doing kind of shared memory GPU where you're evolving a lot of things on a GPU, and maybe you want to solve the QP on the GPU too. So we're looking at that. Yeah, I will end it there, and I'll just thank the people who made this happen. Zach Manchester, my PI at CMU in our lab, Kevin Tracy, who's really was this was his like part of his thesis work, and I'm kind of carrying the torch for it. Andy, who's here, has helped develop this package, and our collaborator Dun Yang, who's at Northwestern, is kind of helping us apply this to quantum control. So if you're curious about kind of where we are in that and want to keep tabs on a paper that will be coming out soon, definitely reach out. Our org is here, so if you want to scan this, you can check out kind of our development hub, and thank you. I'll take some questions.
Cool. Thanks so much for the talk. If anybody has any questions, just put up your hand so I can bring you the mic.
Hi, thanks for the... Hello? Yes, it works now. Okay, great. I have two questions. They're probably horribly naive, so forgive me in advance. You said that this is like derivative-free methods, but I mean, in the fact that you're evolving a bundle of trajectories, doesn't that implicitly mean that you have some sort of finite differencing between the different trajectories? So you're using that as a way to select some optimal trajectory? Is that not correct? Or have I misunderstood something?
Yeah, so I guess when I say this is a derivative-free method, it means at no point do we have to differentiate through the solution of an ODE. So there are derivatives. I mean, like when you solve a QP, you're technically taking gradients of a QP, which is very simple. So derivative-free with an asterisk to say the hard derivatives we don't need to do. The hard derivatives through this dynamics function is what we don't need to handle.
Okay, great.
Yeah.
So I didn't completely misunderstand it. That's good.
Yeah.
The second question that I have is, maybe I don't completely understand the algorithm, but how do you stop? I mean, you had like 100 time steps and I don't know, like 3 dimensions times 2 plus 1, like 7. How do you stop some completely combinatorial explosion of the number of trajectories that you're having to follow? I guess, is there some trimming step at some point where you say, oh, these guys are going in the wrong direction, we forget about them?
Yeah, so that is a great question, and there is definitely a trade-off here. So we're definitely trading off computational costs and like potentially error costs and the errors of the gradients for a memory cost. Yeah. And there's definitely a thing like like this was very overkill a number of time steps.
Right,
so
yeah.
like
Okay.
this was very heavily overkill to get a plot that looked nice because like you can sample this at probably like order 10 and get still a good solution because you're only using the rollouts.
Yeah.
But then the plots don't look very clear. So like I did it in this one for the README, but when we actually do this in practice, yes, we use a very small number, order 5, 10 type of time steps, and then like offload that task. But again, you do definitely have a trade-off in memory when you are storing these bundles, especially in quantum space. Our state dimensions get very big very quickly. But there are a lot of simulators that like potentially aren't differentiable. So, and exactly where this optimality regime lands is something we're working on at the moment.
Okay, thanks.
Does anybody else have, oh, there we go.
I just wanted to help add maybe like 2 other points to maybe clarify some of that, which is like the contrast between like a finite difference and what's going on here. So if Aaron goes back to the slide about kind of affine combinations, so it's actually the fact that like what's going on is it's not a finite difference, which is giving you kind of that like derivative information. It's the fact that you're actually doing this kind of data-driven approach where you're taking these random samples and kind of producing then the manifold from kind of what data pops out. So that gives you kind of like both a little bit of intuition for like that's like a different perspective for how to define this surface. It's like kind of like an input-output structure of like what the dynamical system is whatever the data that is spit out of the dynamical system is. And then like what that gives you is a way to answer your second question about how many points in the bundle do you actually have to worry about, which is like, well, if you start to take random points, eventually you'll kind of saturate the space you need to span. And so you can kind of like think about, you only need as much in the bundle as the space that you're trying to kind of like explore and define and sort of have the ability to interpolate, which is what this affine combination is doing. So it's like a slightly different thing, which has much better properties, especially for things like quantum systems, which is what we work on, for getting that kind of gradient information and approximating the landscape.
And another thing to note is, I should have highlighted this, but this bundle is basically dimension of x times twice the dimension of x, which is kind of essentially the exact same dimension as the Jacobian of a dynamics function. Or so like it's almost like you're storing, it's kind of a Jacobian-esque object, at least in memory, and then you get this extra kind of convex landscape, like another way to approximate the local landscape as opposed to like a Taylor series approximation with a Jacobian. You're using this like convex kind of interpolation space. But yeah, exactly, it's different. So like it's definitely different, and we actually have So in Kevin's work, he has some analysis of this where he shows it is different from a Jacobian or a Taylor series approximation. And like, it's hard to say exactly which is more right or which is wrong. It's just something different, which is kind of interesting. We're working on that at the moment.
Cool. Any other questions from the audience? I'll give people time to think again. Okay, let's thank our speaker again, and we'll come back at 2:30 for a very exciting lightning talk about Trixie CUDA. And if the next speaker would like to get set up now, you're definitely welcome to, or you can come back in 5 minutes.
Cool.
Again, if you need to like run to the washroom or something, we have 5 minutes.
Huh? Yeah. Yeah.
Just wait 5 minutes. I'll prompt you like when you have 5 minutes left and 1 minute left.
Can I start a little bit earlier because I may run all of it. Yeah.
Did anybody actually go out? Like, did anyone? Are we all still here? All right, since we're all still here, and it sounds like there's a lot of exciting content in this talk, we can start a little bit early. So we're next going to hear about Trixie CUDA.jl, and whenever the speaker's ready, you can start.
Okay, thank you so much. Because this talk will also include something about numerical methods, and I will not assume everyone know those mathematical things very well, so I've made those things really simple so that everyone can understand very well. So today I'm going to introduce a new package called Trixie CUDA. And this package works as an accelerator package for another package called Trixie. You can see at the corner. And Trixie is mainly designed for solving hyperbolic PDEs on CPU, but we think it still needs some acceleration on GPU, so that's why we developed this kind of package to offer the GPU support through CUDA.jl. So at this moment, people may ask, why do we have to focus on the hyperbolic PDEs combined with GPU computing? Or in other words, what makes the hyperbolic PDEs, solving this hyperbolic PDEs quite suitable on GPU? So here comes to our two preliminary questions. First, what is hyperbolic PDE? In short, it describes some wave-like behaviors, like the wave equation is its most classic example, and we can see a lot of applications in the fluid dynamics that's related to the hyperbolic PDEs. But what makes the hyperbolic PDEs, solving hyperbolic PDEs quite suitable for GPU computing? Because here we choose a method called discontinuous Garkin method, and we will refer it as DG method later in our talk. What is DG method? And we can take a simple example to quickly look at it. In DG, first we have to, like if we want to solve PDE, like the hyperbolic PDE, first we have to partition the whole space into different elements. Like here, we partition the 1D space into 8 non-overlapping elements. And in each element, we use a polynomial to simulate our solution. And one big thing in DG is that we don't strictly require that the polynomials, like the first polynomial and the second polynomial, we don't require them to like achieve the same value at the element interface. So we can see that here in the circle, the first polynomial are discontinuous, like with the second polynomial. But we cannot just let them be totally separate, because imagine we have a real wave. There must be some information exchange between the first element and the second element. So here we further apply something called numerical flux to do something like the information exchange between these two elements. So just to remember, one big thing in DG is that it allows discontinuity in our final solution. So why it is suitable for solving hyperbolic PDEs? Because hyperbolic PDEs often develop something like a shock or a sharp jump in its final solution. So this kind of scheme are quite suitable for catch those features. But why this kind of scheme is suitable for running on GPU? Because we see here like the whole system. Like we are kind of like solving the solution element by element independently. So you can imagine that the whole system is loosely coupled. So which means we can do this kind of simulation parallelly for each element. So this is what GPU likes. So this kind of methods is quite suitable for solving hyperbolic PDEs on GPU. So here is a short introduction to Trixie CUDA. We want to combine the both good things about Julia and also CUDA. Like Julia is specifically designed for scientific computing, and also we have Julia GPU, which offers us a package called CUDA.jl. And through this CUDA.jl, we can get a fine-grained control over the kernel optimization. And currently, our core acceleration happens in the semi-discretizations. And what is semi-discretization? You can simply view it as the discretization in space, or which means spatial discretization. Typically, if we want to solve a PDE, we do two kinds of discretization. The first is time discretization, and the second is spatial discretization. And people usually, and especially in the software development, we will choose to do the spatial discretization first. Why? Because if we apply a spatial discretization to the PDE, the problem will be reduced to a system of ODEs. So, and we all know that there are quite a lot of well-established methods for solving ODEs. So this saves our efforts for solving PDE. Since in Trixie and Trixie CUDA, we do the spatial discretization first. So that's why we call it semi-discretization. And why do we focus on the semi-discretization? Because of, I mentioned before, the DG methods will reduce the whole system into kind of like a massive matrix-free parallelism. So this is quite suitable for GPU computing. And we can quickly go through the workflow. Like here in the graph, we have a PDE, and then we do the semi-discretization to this PDE problem, and the PDE will be reduced to a system of ODE. Then we apply the solve function to solve this system of ODEs. Then we check the stopping criteria. If it meets the stopping criteria, then we get our final solution. But if no, we have to redo all the things again. So the whole solving steps are done using the iterations. And in Trixie, this kind of semi-discretization process and all the kernels about semi-discretizations are encapsulated into the a function called right-hand side function. So in Trixie CUDA, we renamed this function as right-hand side GPU function to indicate that it encapsulates all the GPU kernels that's related to semi-discretization. And if we break down the semi-discretization into like low-level tasks, we will find it relates something like computing the volume integral, interface flux, and the boundary flux. But I will not go over all these things in a very low detail. So you can see the tutorial here. It talks about DG methods and cover all the low-level details about DG methods. So we can quickly go through an example to say how to use the Trixie CUDA to get the GPU acceleration. Like in the left-hand side, here is an example from Trixie. First, we have to set up the equation and then create solver, set up tree mesh, and create semi-discretization, and also create ODE. And also then we set up callbacks. Then finally we solve this ODE. And in Trixie CUDA, we only have to modify 3 lines of code to get the GPU support. Like here, I marked it in red color. So the user only have to modify the solver, semi-discretization, and ODE. We only have to add the GPU after the original API to get our GPU support. And finally, we run the solve function. You will find it will get accelerated on GPU. So our principle about API design is that we want to make it look similar to the Trixie, and also it intuitively indicates that we get some support from the GPU. So originally, I have some slides about one interesting example about GPU kernel optimization. But last year, in 2023, I gave a 1-hour talk about which heavily focused on the GPU kernel optimization. But I found that if people are not so familiar with the original code, it would be hard for them to follow some low-level details of GPU optimization. And also due to the time limit, I just skipped these 5 slides. But if you are familiar with GPU kernel optimization, in short, it covers example that's about that's triple nested for loop, which contains some dependent for loops. And I use two methods called tiling with shared memory and thread coordinate to optimize this kernel. And there are 3 kinds of tiling algorithms: the block level tiling, warp level tiling, and the register level tiling. So here, this is only first round of our optimization. So I applied the block level tiling algorithms. Sorry, I have no time, so let's just skip here. So let's go directly to our benchmark results. Here, you can see we run our benchmark on the single precision floating point numbers. And here we extract 2 examples for illustration. The first is linear they are all linear advection equations. And the green lines represent the runtime on GPU, and the orange line represents the runtime on CPU. So, and the dashed line represents the median runtime, and the solid line represents the mean value of our runtime. And also, we use this blue shaded area to represent the degrees of freedom. What is degrees of freedom? You can simply view it as our complexity of our problem. Like if you have a high number of degrees of freedom, it means the problem is more complicated. So we can see in the first graph, in the 1D and the 2D dimension problem, the CPU still runs faster than GPU, but in the 3D problem, obviously the GPU runs faster than CPU. But if we increase the complexity for 1D and 2D problem in the second graph, like we see here, the shaded area is almost flat. We can see that the GPU run faster than CPU in all problems, like 1D problem, 2D problem, 3D problems. So we can get a short conclusion that GPU advantage grows with the problem complexity. And here I have a report about the 4 benchmark examples, like we run our benchmarks on all kinds of problems. And also you can use this link to reproduce our benchmarks. So here's some challenge and future directions. The key challenge is that we have a lot of different problems, and for different problems, we have different inputs. And also, we would not assume that all of our users use the same GPU architecture. So it would be very hard to get general optimization across these combinations. And our future directions is to extend the mesh initialization, callbacks, and time-stepping these more steps to GPU. And also, we want to implement mixed precision algorithms. And also, based on the reviewers' comments, I prepared some highlights and gaps in CUDA. So it takes another 5 to 8 minutes. Can I save it later to our discussion session?
Yeah, I think we should stop now and let the next speaker go because we're already over time, and then we can maybe discuss some of this during the panel.
Okay, thank you so much.
So let's thank the speaker.
And also, I want to thank my advisors. They're Henrik, Jesse, and Michael, even though none of them is here today. And also, I want to give my special thanks to Tim. He's super supportive, and also Chris from the scientific machine learning, and also the Julia community. So yeah, and also I'm thinking PhD position for next year. If you see any good opportunities, it would be good if you can let me know. Thank you so much.
Thanks again. And our next talk is going to be project updates about AMD GPU.jl. So whenever the speaker's ready, you can just get started. We're running about 2 minutes behind, so just want to keep things moving.
I'll try to run through a little quickly. I do have a few slides. Good. Thank you. All right. Hello, everyone. This is not a talk written by me. I am taking over for Anton Smirnov, who is the current maintainer of AMD GPU.jl. He wasn't able to make it to JuliaCon this year. I am the original author of AMD GPU.jl. Anton has taken over day-to-day maintenance, but yeah, let's talk about what's new in AMD GPU.jl. That is a mouthful. Okay, so over the last year, we have had a lot of progress in AMD GPU. So there's been about 150 commits from 18 different contributors. That is stellar. That is awesome. Remembering back when I was maintaining it, we did not have as many contributors. That is awesome to see. There's been 31 package releases, and that has been building us up to a 1.0 release, which is awesome. As you can see in this image here from BuildKite, there is 100% reliability in CI. I don't know how that was achieved. That is amazing. But we're basically at the point where no PR gets merged unless CI is green, which is a really nice change. They're testing against official Docker images from AMD upstream and testing on RDNA 3 GPUs, although we do want to get CI running on other GPUs as well, but we'll address that in a little bit. One of the big changes that people will notice is that hardware atomics for floating points is much improved and much faster. So what you can see at the top is an example of using the add atomic macro to increment a value in an array. Before, this was lowering to a cast loop or a compare and swap loop. You do not want to do this. This is not efficient. This is not great. If you have an atomic add instruction, you want to use it. We are now using it. This is awesome to see. This lets you build quite a lot of more advanced algorithms in GPU kernels directly with excellent performance. So enabling this, and one of the key use cases is gradient accumulation. So I believe in the backwards pass, you need to accumulate into a single slot. Thank you. And so extremely important for that. Massive improvements to nerf.jl and Gaussian splatting.jl, both of which Anton develops. One of the other big changes is moving to accelerated kernels.jl. I'm sure plenty of people have heard about this, but accelerated kernels.jl basically provides a bunch of built-in algorithms for all sorts of useful operations on the GPU as kernel abstractions, kernels, and such. So AMD GPU now calls into ak.jl for short for these operations. Better performance, better maintenance situation, just all around much better. Additionally, in the future, we might also move our MapReduce, reverse, and find all implementations into AK in some form or another, which will also be good for the other backends, presumably. I'm not sure if anyone ever ran into this kind of image when working with AMD GPU, but this is quite common on laptops and desktops where you run a kernel or an application and you start using up a lot of GPU memory and suddenly your display manager is not pleased with you. And this, thanks to a new caching memory allocator in AMD GPU, this really does not happen as much for real code, which is awesome to see. And generally, so yeah, you would see stuff like this where the memory just keeps going up, 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 up. And now with this caching allocator, well, it didn't show up here, but you get a flat line. There are still issues with the GC, not running fast enough, but those are work in progress. So yeah, kind of looks like this if you're using it. And yeah, I'll move on from this. Oh yeah, there it is. There's that flat line that I was talking about. So this is great for like machine learning models, AI, all that sort of stuff. Yeah, much better for Gaussian splatting. Again, one of Anton's packages. So hardware enablement, we now have Julia 1.12 support and thus newer LLVM, which is great for performance and hardware support. We support MI300X. Although if anyone from AMD or wherever wants to provide some GPUs for CI, we would love that, or really anything that you can provide. And there's additionally initial enzyme support, although there's still some work to be done there. So you can differentiate through AMD GPU kernels. This is a big one for me. I did a lot of work on this when I was maintainer on, and it never got merged, on being able to actually say when a bounds error happens on the GPU, where did it happen, on which lane, just getting a little bit more information because that first error sucks. So this is beautiful to see. And so this, there's still more work to do. It's hard to do this stuff efficiently, but work in progress. Improved documentation. So moving to Documenter Vitepress. I don't know how to pronounce that. Basically, it's updated documentation. Everything's a lot cleaner, day, night, color changes, whatever, you know what I mean. That's awesome to see. And then, so some future plans are supporting WMMA, basically being able to use built-in matrix multiply hardware and quantization hardware so that you can do these things in Julia kernels, which are very important for all kinds of machine learning and many other kinds of operations. Apparently there's, thank you, flash attention available in an op, and improving that obviously would be big for all sorts of AI machine learning research. Improving enzyme support, multi-GPU programming, which I'm also working on in Dagger, but that's unrelated. And there are some issues with WMMA between GPU generations that need working out. Again, AMD, if you want to help, we would love that. Big shout out to Ludovic Ross, who's been contributing for as long as I can remember. Leonard, Alexis, and all the other contributors. So yeah, thank you so much.
Thanks so much, Julian, for the great talk. So we probably have time for one question while the next speaker, who is me, gets set up. So if somebody wants to handle passing the mic around, go crazy.
And I will do my best to answer your questions, but I'm not fully up to date on everything, so give it a shot.
All right, one quick question. Well, if not, let's thank our speaker again, and we'll let Katie take over shortly.
Thank you. Cool, just give me 1 second here to get the display actually set up. Am I showing up on screen yet? There we go, okay. Let me just mirror very quick. This like never wants to save the fact that I've mirrored my display, it's very annoying. Okay, so as you can see from the title slide, I'm gonna try and give a very quick presentation about what we've made slightly better or added in CUDA.jl in the past year. So I'm one of the CUDA.jl maintainers, obviously like pretty far behind Tim, but hopefully I can give you all a quick overview. So some high-level impressions from the last year. We've had fewer big feature releases for reasons we'll discuss. In fact, we've only had 13 total, including patch versions, since last year's JuliaCon, and we've been at version 5.5.x for nearly a year. So the obvious question for this is to ask whether CUDA.jl development is slowing down. And if you've heard of this so-called Betteridge's law of headlines that says, like, if you ever phrase a headline as a question, the answer is always no. It applies here, so hopefully we can convince you that actually development is proceeding at pace. It's just not as visible on the surface. So one very nice thing about CUDA.jl is our test coverage is up. We've gone up from around like 76% to now 90% over the past year. Of course, this has several knock-on benefits like fixing bugs, better coverage for the library itself, and some stale, unreachable code that was removed. And of course, if anybody knows me, they know I'm one of those like test freaks. The main achievement is that our badge color from CodeCov went from red to green. So we can now feel good about ourselves. If you ever suffer from low self-esteem, getting your coverage badge to go from red to green really helps. We're also, similar to AMD GPU.jl, we're using a lot more functionality from GPU arrays, and we're also trying to move functionality over there so that somewhat optimized methods we've developed for CUDA can now be used to benefit the multiple different backends we now support. So examples of that would be methods like the Chronicle product, A times B times Y, for like matrix vector multiplication, and dot now have backend more or less agnostic implementations in GPU arrays. So these aren't, of course, like super hand-tuned kernels for each device, but it allows us to write code once and reuse it in many locations, and it also gives you, the user or developer, more flexibility. And one thing I just want to mention here, there's a lot of opportunities for new contributors to engage in this kind of development where they offload some methods like MapReduce or sort, for example, from CUDA.jl to kernel abstractions or GPU arrays. So if you're interested in that, stay tuned. We love getting a PR that's net negative lines. Hint, hint, anybody who's here for the hackathon. Please don't delete the entire repo, though. One feature that we have added is support for broadcasting over sparse vectors. You can now broadcast over a cuSparse vector, just like you could with matrices. One thing that is not yet supported for the matrices is broadcasting over a single dimension or doing something like map slices. And also the kernel for the cuSparse vector broadcasting isn't really highly optimized. Like, it works, but there's probably a lot of room for improvement. So if you're an expert in optimizing CUDA kernels, this might be a great opportunity to fix my very bad code. Or if you want to help us out by benchmarking this or contributing a backend agnostic version to kernel abstractions, that might also be great to do. Another feature that we've recently added is avoiding synchronizations in cuBLAS. So our initial implementation, every time you made a call to cuBLAS that accepted a scalar as an argument, like if you were doing some sort of like matrix add, or if your cuBLAS call returns a scalar, like if you're computing the norm, this would actually force device synchronization because of the way the scalars are passed back and forth. And now we've added a wrapper that allows you to store those scalars on the GPU, so there's no synchronization forced, and you can overlap your computations much more easily. And we maintain the initial wrapper implementation, so you don't have to change any of your code. So effectively, what you can do is slightly change the way you're calling cuBLAS, and hopefully see a substantial speed up, but nothing should have broken for you. So as an example, I'll just show here, using CUDA and cuBLAS, you can call the norm2 of some vector here, which is x. And if you provide a cuRef, which is just like a reference to some scalar on the device, you can see that this is not kicked off asynchronously for the first version, which does not use the host located scalar. So it's about 10 times faster. This is obviously a little bit of a contrived example, but it means that hopefully you should be able to make much more effective use of the device. And thank you, Andy. We've also had a lot of smaller, less visible quality of life improvements. So Tim especially, but also many others, have been working very hard to make improvements to the underlying GPU compiler. This is something that doesn't just benefit CUDA, but as one of the more highly used packages, of course, all CUDA users benefit from it. We've been moving wrappers from older library methods to new ones. This has been especially noticeable with cuSparse, I think. We're enabling use of more types. So for all of you machine learning heads out there who really want to use float 16 or brain float 16 or other weird float types that only have like 8 bits in them, we're working hard to enable use of that as we go, and especially as NVIDIA adds more device intrinsics to support that. So a lot of this stuff is like kind of hard to notice, but it's a lot of smaller improvements that add up to make the user experience hopefully more effective for you. There's still a lot of low-hanging fruit that we could target, again, if anybody is looking to contribute to the package. One big one that you've probably noticed is CI instability. So our build is unfortunately failing somewhat regularly for not obvious reasons. For example, just today we were trying to upgrade a driver version for GPU CI, and it randomly starts ooming the test server for reasons that I don't think we understand. So if you understand why that might be happening or want to investigate it, that would be awesome. We also, I mean, this is also a result of the fact that we do a lot of comprehensive testing of CUDA.jl, so it's in a way a good problem to have that we're catching edge cases that could affect you if you're running on like an older system, for example. Some of our wrappers spend a really long time pre-compiling because we have way too much specialization. This is especially a problem in cuSparse, but there's other places it occurs as well. So if someone wants to go in and sprinkle a bunch of no specializes in a judicious way, that would be very welcome. If you go look at our issues page, we have a lot of bad behavior that's related to views. This is, again, kind of a low-hanging fruit for someone to target if they want to figure out why our like matrix multiplication kernel keeps breaking with views. And of course, one thing that we always need more of is benchmarking and comparison of the kernels that we've written in the library, both with some of the other libraries that like we maintain in the ecosystem, but then also with CPU methods and other state-of-the-art GPU libraries, so we can see how we're measuring up and hopefully figure out what our priorities should be. So one thing I think we'd be very interested from hearing from the users, because we know CUDA.jl is probably one of the more wider used GPU packages in Julia, is what is it that you want? So of course I have my own opinions, and I'm sure Tim does as well, about like what I would find interesting to work on, but ultimately it's the users of the package who should drive at least some of the development, hopefully. So we're going to have a panel later today, and hopefully you can give us all of your feedback about what you don't like, what you love, and what things you would like added. And so we'll be discussing this later. And also, just want to mention, if you're here on Saturday, we will definitely have a lot of GPU folks around if you want to get started contributing or just want to complain or tell us how wonderful everything is. So please come find us at the hackathon. And with that, I will end. And I think hopefully our accelerated kernel speaker is ready. But in the meantime, we can probably do like a question or two. So thank you.
Yeah, we have a question.
So maybe that goes both for CUDA and AMD.jl. I was just in this reaction talk with this wonderful world of everything being tiled and optimized and distributed, and we use CUDA, but for the code generation, how can this come together? Will this come together? What's the path forward with these different ways of talking to the GPU?
So I'm not super familiar with reactant, so I don't want to say anything too strong, but I think also the next talk is going to address part of this. So why don't we discuss this further during the panel, is my non-answer to your question.
Okay. All right. Do you want to take back over emceeing, or once you're settled? Okay. Yeah.
Also, sorry, we can't have the AC on, because otherwise you wouldn't be able to hear the pod, but it is hot in here. We apologize.
Oh. Yeah. Yeah, absolutely. All right, let's welcome Leonard, our next speaker.
Perfect. Everyone can hear me okay? Yeah, cool. Right, so hi everyone, I'm Leonard Kushan, and today I'm going to be talking about accelerator kernels.jl. But more importantly, what you can build with it and how. So currently, the approaches we have for cross-architecture algorithms kind of looks like that. You have an algorithm that has CPU sections, and then some parts you can just offload onto your GPU or PU kind of accelerator. How do we make this transition from cross-architecture to multi-architecture code that works on all platforms simultaneously? So I want my code to be working on CPUs on laptops, on GPUs on desktops, on CPUs and GPUs on workstations, and I want every possible combination of that via MPI on clusters. So some nodes with CPUs, some nodes with GPUs. Sounds idealistic, right? But actually we can do that. So in order for it, we need to have these 4 levels of parallelism. So you've got the instruction level ones, so single instruction, multiple data. You have your shared memory multi-threading on your CPUs. You have your accelerator parallelism, GPUs or TPUs or whatever comes in the future. And your distributed parallelism. And for multi-architecture, we want all of them to be working simultaneously. So these are some particles in a simulation we're running. I'm more familiar with particles, but it kind of would look like that. You have a domain, a part of it runs on the GPU, a part of it on a CPU, and then you have these MPI layer for communication. Or if you're more used to dealing with Eulerian type data, so your CFD simulations, your FEM, or what have you, discretizations, I'd like to have parts of it running on CPUs, parts of it running on GPUs, and everything all together all at once. So let's take them one by one. We have our instruction level sim. That's kind of solved by working with your compiler, and the performance guidelines are really excellent. You have your shared memory multi-threading. So in this case, most implementations coalesce into a few kind of similar approaches. So these days, it's really quite accessible and high level. You can write really high level code for your multi-threading stuff. Accelerator parallelism. Here we're kind of in the Middle Ages compared to CPU compilers. You really need high effort, very different styles of programming, and you often end up being locked into your vendor. So it's a huge task to port your code onto GPUs. Indeed, many codes these days just write themselves for GPU acceleration only, and they don't even work on CPUs because there is that very high entry. And then your distributed parallelism, for better or worse, MPI is the best approach for it in the sense that it's the only one that's performant. Nothing higher level than that really took off yet, but hopefully distributed next might be having a word at that. It's difficult and idiosyncratic, but it's reliable. It's kind of a solved problem since the 90s. So altogether, all at once, this is kind of the terra incognita, right? Not much work has been done in this space, and actually this is where Julia really could shine and be able to write the next-gen applications. So, with that in mind, in this talk, I'm going to be talking about the current state of parallel approaches, compilation models and why Julia is the right tool for this kind of job, some benchmarks, and we can be faster than C, which was surprising. Applications and performance, so how you can do CPU, GPU co-processing and all that. A bit about the algorithm building blocks, and in the end, how to write transparently and transparent multi-architecture code. So more than anything, I want, with this talk, to make a call to the Julia community to be writing, or taking into consideration, writing more applications with this sort of multi-architecturality in mind. In terms of audience, so in high-performance computing, the knowledge is often quite siloed. So some people are absolute wizards in something, but what might seem basic to them often looks arcane from the outside. So I'm expecting a mixed audience. There will be things that I'm providing for context and details. Some parts you might know, some parts, in the end, they all build up towards what we can do in the end. So the aim is not really to preach to believers, but again, make a call into writing more multi-architecture libraries. So not just accelerated kernels, but what you can build on top of them, because that's in the end what matters. And again, we have this unique opportunity in Julia to write uniquely future-proof performant applications. So let's go a bit into the current cross-architecture programming models. So the kind of degrees of freedom that we have in the space are the types of programming models, whether they're standards-based, API-based, or language-based, or whether transpiler, the kind of hardware it supports, whether you have access to intrinsics, so inner memory hierarchies, bit-level operations, atomic, stuff like that, and the complexity, both for an implementer and for someone to use it. Information on this is quite disparate on the internet. So this, I don't know, a few years ago when I first started looking into accelerating stuff, it took a long while to just get information, and they were all, again, very siloed. So this is my overview of how these programming models work and why Julia is unique in this aspect. So, standards. These are like abstract frameworks that are defined as sets of APIs and libraries and compilers, and these are then left for vendors to implement. So you have things like OpenCL, OpenMP, Open yada yada, SYCL, and that. The important part is that you're kind of at the mercy of your vendor to actually implement something good. OpenCL these days is pretty good, but a few years ago, it suffered from performance compared to CUDA on NVIDIA hardware. In terms of usage, they have separate source kernels, which kind of look like that. You often program either on strings or separate files. Anyways, they need to be separate, and on the internet, people cite this as a big annoyance for why it didn't really take off in scientific computing. Not sure that SYCL does much better than that, but hey-oh. You have, on the other end, these commented directives approaches like OpenMP or OpenACC, which look nice. You just add a comment and pray that it works. And then you have SYCL, which are called single source kernels. Slightly higher level, but not really high level code, especially for scientific computing. In terms of supported hardware, it kind of looks like that. Nothing really shines everywhere except for Vulkan, which is incredibly boilerplate heavy, and there is not a single scientific library that I know of written in Vulkan. In terms of intrinsics, of course, the directive-based ones don't give you access to that because they need to be outside of your code, and everything else it does. In terms of the burden, everything here is high for the implementer. They are standards-based. You expect someone else to go and actually implement it for you and hope that they do a good job. In terms of usability, kind of looks like that. The directive ones are easy, of course, but very limited. You have API-based approaches like Cocos, Raja, Arrayfire. You have a unified library interface, which effectively just forwards calls to different existing implementations. APIs look slightly higher level, and you also have things in Python like Arrayfire. Supported hardware, we do a bit better here except for Apple. And intrinsics, you don't really have access to those here because it needs to forward things to other libraries. And the burden and the complexities are kind of medium overall, because you don't have to implement things yourself, but you need to maintain forwards to other libraries. And finally, you have your domain-specific languages or esoteric programming languages for kernel writing. So these are more recent things like Halide, Fatark, Bend, and these kind of runtimes. And they look slightly higher level, but in the end, under the hood, what they do is just have immutable constructs that you put together to kind of create a directed acyclic graph, kind of what Dask and Dagger are doing. But in the end, you are tied to just things that can be expressed this way. So you have that kind of task graph. This is from Dask, but it's kind of the same. And in terms of supported hardware, again, quite mixed. And intrinsics, of course, not. And you're quite limited. So at this point, having gone through all of this, the irony is not completely lost. You have this classic joke, you've got 14 competing standards, where someone says, oh, this is ridiculous, we need something that merges them all together, and we can do everything all together at once. And now we have 15 competing standards. Hopefully by the end of this, you'll see that there are unique aspects to what we have in Julia. So for that, bit of background in when you're writing simulations, like scientific code in Julia, you have, not just Julia, but in general, you have these two approaches. I come from a chemical engineering background, and I run CFD simulations, FEM, and discrete element method, if that rings a bell to anyone. But this is what I've seen across the entire spectrum. So you have, on one end, the fast engines, which are written in a low-level language, like C, C++, or Fortran. Steep learning curve, very difficult to add functionality, especially if you're not a computer scientist. Most people are PhDs or engineers who want to solve a problem, not figure out binary compatibility. And to drive a simulation, you have either a higher level scripting language or clunky parameter files, or you compile everything yourself, so that's C++ and not very easy for engineers. But they can simulate industrial scale, real world problems. The other, and you have your convenient engines written in something like Python or MATLAB, sometimes R. Easy to use, easy to add functionality, and they're a good research platform for small things. But they are limited to small cases, and that's the biggest issue. And because of that, everyone kind of implements their own thing. So you have a very fragmented community. This is a 2024 paper that says there is a lack of tools that provide friendly environment for testing discrete element method, kind of like molecular dynamics, particles, in simple scenarios. And that's yet another entire simulation engine written in MATLAB, and we can do better. So how to write such a fast numerical engine? The joke is not using C++. It's a lot more fun saying this to physics or engineering communities. But the idea is that you should be using the right tool for the job. And I would argue that C, C++, and Fortran, these ones, saying this for anyone who might be watching this on YouTube later on, the idea is that these are not really the languages for performance. They are the languages for low-level control. That's what they give you. There is correlation on a Venn diagram between low-level control and fast numerics, but that's not necessarily what you need. So in your classical compilation model, you have your individual files that you compile individually, called translation units in C++ parlance. You optimize each file individually, and then you have your linker to put them all together. The idea is that if one file changes, you only have to compile that and then do the linking step. And this makes absolute sense for what they were made to solve, C, C++, and Fortran. If you're writing an operating system with a million files, you don't want to be recompiling everything every single time. But of course, you're very limited in the kind of optimization you can do across these files. In Julia, you have all these scripts where you have some of functions that you will put together into your script that you'll be calling, and then effectively it's as if everything is compiled at once globally, and that means that we have a lot more information available to the compiler, and that's critical for numerical code. So here we have this the simulation engine that you build, either in C++ or whatever, it's not the end goal. It's what you build with it, really, that matters. So in that sense, it's the composability that you care the most. Not when you're building a product, like a operating system or a browser, but when you're building engineering tools, simulations, things to aid discovery. And that's where they need that kind of composability. In my mind, I split simulations or engines like this into two stages. You have the simulation setup, and then you have the simulation runtime. If you think of like a CFD simulation, you can spend a lot of time putting together your matrices and building things up, because then when you press go, everything reduces down to matrix multiplications, which are simple enough to optimize, or it's a known problem. You go anything higher level than that, and then you want to couple them to optimizers, you want to do surrogate models, you want to do approximations, you want to do yada yada, and suddenly that kind of setup really matters. So for the runtime performance, C and C++ work great. For the setup, not so much. So that's why that's what I've built accelerator kernels. And then it can take any code, and it doesn't have to be tied to any backend. So you have your base Julia compilation via LLVM, and then via kernel abstractions and GPU compiler and all that incredible infrastructure, really unique infrastructure that we have. We can, importantly, transpile all of this code to the target architecture, and then, importantly, benefit from all the optimizations on these native platforms. And that's what you really want for performance. So I can have my cake and eat it too. That's the whole idea. So here you have your normal CPU code, and for a simple, embarrassingly parallel loop like that, all you have to do is change that one line. And that will have optimal performance on both CPUs and GPUs. And I'm going to show you that in a second. But the important part, there is no special casing, no part of my code, and I want this, no part of my code to be specialized for CPUs or AMD or CUDA or whatnot. I want to write it once, and I want it to work everywhere, and I want it to be future-proof, and I want to have the performance improvements of the future in it. So this is the huge table that you'll find in the paper. Don't need to go through it now, but this approach that we have at the bottom kind of gives us the best of all worlds for the purposes of writing scientific code. Some benchmarks. We have this arithmetics code, so a molecular dynamics potential that I took. It's fairly simple code, and that's the C version with OpenMP. Beautiful part of Julia is that I can run the exact same matrices, the exact same data layout, pass it to C. And same thing in Julia. And these are the findings. So both on a Mac, on an ARM, and on an Intel CPU, the basic version written in C is really slow, which looked very weird. So I had to go into it. So I had to investigate the disassembled code. Most people, when they write in C and C++, or most engineers that I know of at least, they just assume that if you write something in C and C++, it will automatically be fast, especially for numerics. But how many of them actually look into what comes out the other end? So I had to go through the disassembled code to figure out that, oh, these powers are actually not computed as integer powers, but you call the floating point routine from glibc. So then I have to change that and manually write my powers, and that's how you get the performance back on the right. But it's still really not, it's kind of on par with what you get from Julia. But the important part is that you have a much lower entry in Julia that you can follow through your code via Cthulhu. You can look at your typed code, you can look at what comes out, and it's annotated. And for multi-threaded code, this is what you have in accelerator kernels, a very young library based on a very young programming language compared to OpenMP, the most well-adopted multi-threaded package. and they're on par. So yes, you can have that performance. For GPU benchmarks, I've put everything in the GitHub repository, including the disassembled files, and also in the accelerated kernels paper. I'll show that at the end on archive. But the important part is that we want to make this transition from, okay, my code can run on a CPU or on a GPU, to running on a CPU and a GPU simultaneously. So let's take a non-trivial problem, something that's not really embarrassingly parallel. It's simple to split my for loop into two if I really wanted that. But let's take sorting, something that needs communication. So I can have my CPU data and I have my accelerator data completely separately. And I can use MPI sort, a library that I've written, for this kind of simultaneous multi-device sorting. It really looks as simple as that to do that kind of multi-architecture code. I can do on one rank a normal array, and then the other I can have a rock array. And then I have the MPI communication layer that does the transparent CPU-GPU data transfer, because MPI already has that. And that's kind of it. Like, accelerated kernels doesn't need to know about MPI sort doesn't need to know about accelerated kernels, but you have this kind of unique interoperability between libraries thanks to the Julia compilation model. And you have the performance as well. So we've had a benchmark on 200 GPUs on a cluster in Birmingham called Baskerville. And the current record stands at 900 gigabytes per second sorting throughput on 262,144 CPU cores of what was at the time the fastest supercomputer in the world. Now we can have a tier 2 supercomputer in a town in the UK and get really close to that in a high-level programming language. And you have your weak scaling, which tapers and becomes kind of linear. Very good scaling. Strong scaling, it's okay. You still get performance improvements by adding new GPUs to the same problem, but diminishing returns, of course. And with this project, where we benchmark the supercomputer, it was actually interesting to find that if you do multi-GPU programming for communication-heavy tasks, really they only become cost-effective if you'd have your GPU interconnects. That was an interesting finding in the paper, but the idea is I didn't have to change anything in the code. It worked transparently with that MPI implementation from the supercomputer. So in accelerated kernels, you have all of these building blocks that I would argue cover 90% of the use cases. So you have your abstract general loops, and you have your maps and your sorts and your reductions and accumulations and searches and arithmetics, and that's kind of it really. So how much code duplication will I need to be able to write this kind of multi-architecture code? For your specialized algorithms like sort, reduce, the fundamental things. At the instruction level, these are largely handled by compilers, so no code duplication you need there. This is a bit of a contentious point, I suppose. You have the shared memory multi-threading on CPU. So you have excellent performance with the base Julia threads. They really do. You've seen in that benchmark comparable with OpenMP. But you have very different trade-offs compared to GPUs. CPU threads are expensive to spawn, so each thread should be doing as much work as possible and use the minimum number of threads, just that many, before shutting down. GPU threads, on the other hand, are cheap. You should be using as many threads as you can. CPU atomics are quite expensive, especially for floating point atomics. Most CPUs don't have actually native atomics for floating point code. They compile that down into a compare and exchange loop. Whereas GPUs actually were built from the ground up to have floating point atomics, so they're pretty good. And on GPUs you have 3 cache levels. You have your device memory, your block memory, and then your thread memory, and you have direct access to them, and you should be using them if you want good throughput. So really these kind of core algorithms like sort, reduce, accumulate, they really do have to be designed very differently between CPUs and GPUs. And that would often need this kind of code duplication. But only really for these kind of specialized algorithms. And thanks to kernel abstractions and GPU compiler, you can actually write those once. And that's what accelerated kernels provides. And then for your distributed parallelism, you just need to define your rank data separation and your communication points. No, you only do that once. So to get the multi-architecture benefit, your device parallelism, CPU, GPU, can be composed with the MPI communication layer. The CUDA or ROCm aware MPI implementations transparently work on both laptops and supercomputers. That's the beauty of it. It works transparently. And you need no special casing, thanks to the Julia composability between all of those. You get all the permutations. So for general purpose code, I would argue that 90% of it could be written as a combination of sort, map, reduce, and accumulate, and your custom parallel loops, like the for each index. And MPI.jl is the nicest interface I've seen to MPI. It really reduces the kind of MPI repeats that you have to do in order to use it in C or C++. So how much do we actually need to be writing these kind of multi-architecture libraries? You can start with your accelerated kernels general code, and you can write your algorithms directly like that, where you have a normal for loop, stick an AK for loop. Optional for specialized algorithms like ray tracing, where you do need direct access to things like maybe, well, not really atomics, they do work, but the caching. You could write the kernels in kernel abstractions, and you can further reduce duplication by extracting your general code into functions and then just calling them within your kernels, and they'll be inlined and you get the benefits. And then finally, you can add an MPI communication layer. And between these three building blocks, accelerated kernels, optionally kernel abstractions, and MPI, you get high performance code on all permutations of x86 or ARM CPUs, on Windows, Linux, Mac, and on accelerators from AMD, NVIDIA, Intel One API, to Apple, to architectures from laptops to supercomputers, and every combination between those kind of for free. And that's really the beauty of it, and that's my call to the Julia community. The paper, you'll find the manuscript on archive. If you want it, you can Google it. It comes up easily. You also have the benchmarks that I've run for this. So, in the end, Julia is really in a unique place to create future-proof, next-generation multi-architecture codes because of the unique composability that it gives you. And you have these three building blocks: accelerated kernels for high-performance back-end agnostic code. Internally, this will use the best CPU and GPU algorithms available, and you've seen they are comparable to state-of-the-art. For specialized things, like where you might need intrinsics, you might need to write things in kernel abstractions, though more intrinsics will be added to kernel abstractions, things like shuffle instructions and so on, should you need those. And an MPI communication layer. And that's it. And really the beautiful part of it is that you have this incredibly vibrant community. For me, I've been writing libraries for many years. I was a C programmer by training, libraries in Python, Rust, C, and so on. But never have they actually been so readily adopted and so many people contributing to them as here, and you have your Slack channels, your issues, and so on. So anyone watching this at a later date, do use them. Everyone's really lovely in Julia. So that's it from my side. If you have any questions, I'm happy to answer them now or later, and thank you very much. Write multi-architecture code.
Okay, so we probably have time for one question before the panel, so if anybody has a question.
So how far are you going to go with accelerated kernels, and where are you going to stop? Like, what are you interested in implementing there, and what are you kind of feeling like this is the line? Like linear algebra kernels, for example, is something we're looking at for Dagger because we need those for our big parallel algorithms.
Mhm.
What are your thoughts on that?
I would genuinely like to have them in accelerator kernels. So at the moment, it has these fundamental building blocks. I would like to add to it as soon as possible things like random number generators, because currently in many parts of the Julia GPU community, you need to forward calls to vendor libraries like Thrust and so on. It would be nice to have random number generators that are agnostic to everything. Would like to see how composable that would be with distributions.jl, if you can find a way to make them work together. And then linear algebra, sure. We can look into the scope of what they would be. There are also talks of having accelerated kernels as a backend for algorithms to Julia compiler. If that will be the case, it will maybe have to be a bit smaller as a footprint. So we might do accelerated kernels, accelerated maths or something for the linear algebra. Again, I'm very happy to discuss with the community and coordinate and see which way would be best to go.
Awesome, thank you.
That's right.
All right, so let's thank our speaker again for the really great talk. So now we were going to do like a panel with the Julia GPU developers, like broadly defined. So if, Andre, if you want to leave, like of course I can't stop you from leaving, but if you would like to stay and be part of the panel, you're welcome to as well. Similarly, like I don't know if Tim wants to get up, you don't have to. Or Julian also, since you also developed that. Or anyone who considers themselves a GPU contributor. It's like very ecumenical here, I guess. I'm also going to post, if you're in the pound GPU channel on Julia Slack, I made a little hackMD that hopefully everyone can edit. Please tell me if you can't see and edit it. And that way we can like gather some notes from what everyone thinks. The other thing, just as people are leaving, we do have the closing ceremony at 4:10 p.m. in David Lawrence 121. So please go there. We'll be giving out the community awards. So after this, we'll head over to David Lawrence. Wow, that took me like 5 tries to say David. Anyway, yeah. Developers, please come up and I'll try and connect to the projector again. Yeah, so we're trying to do this panel style. So I guess like the goal here was to hear like your feedback about the Julia GPU ecosystem, like requests, things that people like, things that people wish they had, things that everyone thinks is incredible and amazing. So just go crazy with it while I hook up my display.
I'm guessing we should start with Oliver's question from a second ago about the integration with Reactant.
You can be if
I
you
think
want.
that all remains to be seen because it's a separate array type, it's a separate infrastructure, it's MLIR based, not LLVM based. So it's a completely different way of tackling things, and it really remains to be seen how widely applicable Reactant will be. Will it be will it just work out of the box with all of the existing GPU codes that we have, or will there still be a role for a GPU arrays-based stuff? I presume there will be. So figuring out where that boundary is I think the first step before deciding or figuring out how to compose both approaches to GPU computing. So remains to be seen at this point.
Stay down there.
We just have that one. So here, I can also move this
That's
one.
fine. I just basically wanted to say thank you, because when I show Julia to people or try to convince people that Julia might be a good idea, just being able to demonstrate that, oh, by the way, this broadcast, you just change the array type and then it runs on a GPU. Or like, I work with a young master student and she has the likelihood, and she's not that deep into computing yet, but she's getting there, but just going on a GPU was so easy. And now she's just in generally what this GPU availability for the language has done, yeah, just thank you.
Yay.
Oh, nice.
Okay, yeah, we can pass this around. Also, as you can see, I'm taking notes, and hopefully everyone has access to this, so if I quoted you wrong, please just edit what I wrote down as notes for what you said.
Nice. Okay.
I have a in-ecosystem question and like a intra-ecosystem question. I'll ask the intra-ecosystem question first. With the added new Julia C static compilation, how do we envision where people might want to compile a workload that depends on GPU? Let's just assume that they know exactly everything about the platform they're going to run their code, but that involves GPU. Is that beyond horizon?
Not right. Work? Okay. Compiling the GPU stack with Julia C is currently not an option because of the limitations that Julia C imposes. Everything has to be fully statically compilable, which is completely fine for the GPU kernels themselves, which have to be statically compiled. But the whole runtime surrounding it, i.e. CUDA.jl itself or GPU RAIDs.jl itself, those are chock full with dynamic dispatches in places that don't matter because it's not the hot part of the code. So having to optimize all that to fit the standards of Julia C is not going to happen soon-ish. I'm guessing at some point maybe Julia C itself is still in heavy development, so there might be the requirements of code might be relaxed from the Julia C side as well, at which point it might be more feasible to make the GPU stack statically compilable. Yeah.
My understanding is if you use the unsafe, it's possible to give it a workload where it would just compile everything the workload hits. Would that at least be a technically workable?
I haven't experimented with it myself, but kernel launches and the way we integrate, it does have some inherent dynamic dispatches in there, which I don't think you can just compile and trace away. But I should have to test it myself. I don't have experience with it. In any case, I mean, we at this point, we even still have some issues with regular pre-compilation workloads. So I'm guessing that might be the first step to tackle before jumping onto the full, let's generate a binary out of the whole GPU stack approach.
So we had to cut off the Trixie CUDA talk earlier, but I know the speaker had some feedback for the developers, so maybe we could talk about that now, since there seemed to be a lot. I don't know if you want to like put it up on the screen or just tell us what it was, or. Yeah, we can quickly show the screen and then swap back and forth. We'll make this work somehow. This is like if you've ever had to use multiple devices in CUDA, like this is exactly how painful it is. So we're really making it work here, folks. How many core developers does it take to switch display sources for a talk? Okay, we're good. We got it. Is this showing up? Yes, okay, you're on the screen.
Yeah, we can go back to ours.
Aha, here we go. Beautiful. This is what we were hoping for.
Yeah. I think the CUDA is most powerful for its ecosystem. And I found that CUDA.jl are quite good doing something about like package support, like it wraps functions in QBLAS and QFFT, QSolver, and so on. And here I may think I need some support from like for our users, like we can choose the standard math functions or between the intrinsic functions. Like we can see the reference like in CUDA. Basically, it offers two kinds of mathematical functions. The first one is standard functions. The second is intrinsic functions. I guess in CUDA.jl we are default to use standard functions, right? Yeah. So I I hope you can offer some support, like we can choose the intrinsic functions.
Yeah, that's tricky.
Yeah, please use the mic.
Wait, yeah, here you go.
Yeah, I guess the point being made is like being able to choose for, say, if you do x divided by y, you know, which function does that actually call? Does that call the implementation in LLVM if you just emit a div instruction in LLVM, or is it calling something in libdevice provided by NVIDIA? Is there the opportunity to actually like change that? And I know there are issues with semantics around one implementation providing certain semantics, another providing other ones. So Tim knows more about this.
Yeah, so in general, we always try to pick functions such that we respect Julia's semantics. So especially with respect to floating point semantics, NAND propagation, and so on. We start out by trying to use NVIDIA's functionality from libdevice, for example, but when we notice that there's disagreements between the semantics that Julia typically has for its standard library functions and what is being provided by the NVIDIA standard library, we move away from the libdevice functionality to custom functionality, such that we think it's more important, or at least the reasoning is that it's more important that you can compose or port existing code to the GPU and have it execute correctly, rather than get 100% of the performance out of the device that's available. Making that configurable is non-trivial, and I'm not sure it's worth it. But I mean, users, please correct me if I'm wrong. But so the trade-off is performance versus correctness, and up until this point, it has been mostly on the correctness area, making it easier to port code rather than making it easier to extract all performance. So the note was how much performance is missing. I think that heavily depends on the kind of application. Most of the time, 0, because GPUs are exceptionally good at hiding the performance of additional arithmetic operations anyway, and hiding it behind some memory load that needs to happen anyway. But if you have a kernel where you're bottlenecked on arithmetic, and then switching from the high performance intrinsics to a slightly lower performance one may have an impact, but I wouldn't dare to say what percentage of difference that would make. Highly depends on the kernel. And to some extent, we already have a minor version of configurability, and that's by using fastmath. So we do implement the fastmath versions of math intrinsics. The problem is that this is a fairly crude tool just because of how it's implemented in Julia itself. It's a purely syntactical transformation by sticking at fastmath around a certain block of code, whereas that could be something more fine-grained at the compiler's level. But that would first need to be something that would have to be implemented in base, I would rather guess, than bolting it onto the GPU stack as some custom functionality.
Would you have any examples of, well, with fastmath you have the checked versions and the unchecked versions. Any other examples of where this kind of fine-grained?
Well, all of the math intrinsics. Every trigonometric function has a fastmath equivalent. That's not necessarily checked unchecked, but it does dispatch to lower precision functions with a higher rate of error. That, for example, in the case of some GPUs do actually have a coprocessor which can execute certain high-level math functionality. Generally, we do not dispatch to them because they're wildly imprecise, especially compared to what Julia math functionality delivers out of the box. But with fast math, we do dispatch to those, so that can make a difference.
Thank you.
Oh.
Also, we got a couple more things you wanted to oh, yes. Okay.
Yeah, and also, like, we can support, I hope you can support more types. Like here, like CUDA, C++, they provide some vector types. like I found the flow 4 is super useful, so I can. But this is not a big problem for me. So if I want to use them, I can make a PR to like contribute to CUDA.jl. What I found is really problematic is the tool ecosystem. I find that Julia GPU are kind of running behind, like it's not matched so well with the CUDA tools ecosystem. Like I can take a quick example. Oh, sorry, I don't know this one. Like if I want to profile this really complicated kernels, and I try to run, this session is already attached by the inside compute. So let's say this is doing the profiling. It takes some time. And this is the kernel we want to look at. Like here, the inside compute gives some suggestions. Like we can just ignore the first suggestion because I'm mainly running on double precision, and it suggests me to use the single precision. What the main problem is the uncoalesced shared memory access. Can you see it clearly?
It's a little small, but...
Yeah, but it suggests me there is some problem in the shared memory access. So we go to this kernel and check this. And see here the memory throughput is really bad. So there must be some problem with our shared memory accessing. So then I check the source code. Let's see, we look at the assembly code, and we can just search for something like LDS, and I will explain what is LDS. LD means load memory, and S means shared memory. So we mainly have to, if there is some problem with our shared memory accessing pattern, we mainly have to search. If we want to locate it in our assembly code, we mainly have to search for LDS or STS. STS means store some memory to the shared memory. So if we search LDS and it helps us locate something like, here we can see some warning signs, and it indicates that there's some problem with these lines of assembly code. So next I want to do is to map this, locate which line of source code is actually have the problem. So if we locate this one, it's all mapped to something
that's a no deficiency.
Yeah.
That's no issue in LLVM, and we've asked NVIDIA to help us about that. But that's a known issue.
Yeah, and this problem has trapped me for a really, really long time. And if we actually look at the real custom kernels, it's just nothing about the problems. Like it's all showing some branching problems, and I cannot locate the problem in my code.
Yeah, it's a known issue. And for some context, the reason is that Julia relies heavily on inlining, whereas the debug information is only attached to the innermost frame. So that means that if you have a kernel that, for example, does array indexing is expensive. All of the frames will be attached to the implementation of getIndex and not of the caller frame, which calls getIndex. That's because, again, everything is highly sensitive on inlining. The debug info does retain all of the frames where the code comes from and how it was inlined, but that's not retained in the generated PTX assembly, even though PTX does support that. So we're in touch with NVIDIA to try and add that functionality to the MVPTX backend, such that tools can ingest all of the information regarding inlining and more correctly allow attributing the cost of certain operations in tools such like Insight Compute.
Awesome.
I just hope we can get more support from the tool ecosystem.
Yeah. Yeah, I think that would be very helpful. I just want to also keep us aware of time because we've got about 10 minutes left, and I think all of us could probably like discuss LLVM support like all day, but it would also be great to hear from the wider ecosystem of people who are here and maybe aren't all CUDA users. So if you have folks in the audience who have a question.
Did you have one also?
Just concerning what was talked about before about the types that were supported. So for indexing in 32, it's only partially supported still, right? Is that on the horizon to support that anytime soon, like fully?
There wasn't anything keeping the PR back, so it just needs somebody to finish it up and make sure that it passes all tests. It should be relatively straightforward work, or at least insofar that we tackle the problem from within CUDA.jl. Julia itself supporting 32-bit indexing is probably not going to happen. That is a very, very large change to machinery that very few people fully understand. So it's going to be tricky to make sure that Julia itself can properly perform 32-bit indexing, but with sufficient overrides, we can do a fairly good job from within CUDA.jl itself. And you know which prototype PR I'm talking about, and at this point, it just needs somebody to go in, run the test suite, see where the failures come from, and debug as appropriate. But in principle, there's nothing holding it back.
Okay, thanks.
Sorry, I have got a question on that. What exactly do you mean by supporting the 32-bit integer indexing in at that level? Do you mean like having the integer literals that you write for indexing, say array brackets 1, that 1 not being a 64-bit integer as it is in Julia by default?
Yes, and the problem is that we rely on functionality from base. So if you call getIndex, there's multiple layers of indexing in between you providing a literal to the square brackets and it's calling the innermost getIndex call and making sure that the 32-bitness of the integer is preserved all the way through. That is something tricky that in Julia is difficult because we generally use the machine native int type in all of these definitions. Expanding that to the full integer type, which can be any kind of integer, opens up the core to lots of potential ambiguities, and that would be a fairly tricky change to get into base. We've worked around that by sufficiently re-implementing enough of the indexing stack in CUDA.jl itself as such to preserve the type of the literal that you provide to the square brackets. But there are still corner cases where that will not work. For example, when using views or when using derived array types, we may still rely on certain indexing functionality from base. It's only specialized for the CUDA device array type.
Do we have another audience question? Can you guys raise your hands a little higher? Sorry, I think it can be hard to see. Okay, there's another one there.
Yeah, I wanted to ask what's the state of oneAPI.jl? Apparently it's looking for maintenance, so this could be a good way to find some.
OneAPI.jl is in a tricky spot because of multiple things, primarily Intel not doing all that well right now. And they funded the development of me working on the back end. So that funding has disappeared, meaning that I have to spend my time equally on oneAPI as well as the other backends based on the amount of users. And oneAPI has very few users, sadly. It's definitely not unmaintained, so it's still part of CI. It's still being tested as a reverse CI in some of the in GPU compiler, GPU arrays, and so on and so forth. But it's definitely on the low end scale of developer maintenance, at least from my side. I mean, the community is happy to take it up and continue some of the work there. But from my side, I'm not investing as much time anymore as I was last year. Similarly, I guess it's also waiting to see what Intel is going to do about OneAPI stack itself, which is why I'm also not putting too much effort in it, even especially if maybe OpenCL may end again up the way to program Intel GPUs in the future. So that's all remain to be seen, and that kind of uncertainty puts it in a slightly tricky position.
Related, where should a more advanced user, let's say, contribute to harmonize these different capabilities of backend? Because right now we are running into a problem where Metal does not have Atomic's floating point addition onto their shared memory, so which means we probably want a different lowering to a CAS loop in Atomics, but it's not clear to us even if we want and have the capability to make the contribution, where and how that should happen.
The answer to the first half of your question was easy. That's porting stuff to GPU-raised.gl, but support for Atomics is something very low level that needs to happen in the backends themselves. For Atomics specifically, there's two possible routes that we're exploring. The one is continuing with the current approach of abstracting functionality in atomics.gl and unsafe atomics, which is one of the packages that was developed as a common base of atomic functionality. We could put, or there could be put some functionality there that specializes based on the backend as to dispatch to then either compare and swap loop or a native implementation. It currently does not have that functionality, so it's always going to try and dispatch to the, for example, atomic add function, even though it might not be supported for certain types. That's problematic, so the quick fix would be to make atomics.gl smarter. The long-term fix, we think, is try to rely more on LLVM atomics and then legalize them as part of a pass in GPU compiler, such that all of the backends are just going to emit plain atomic operations. Ideally, that also makes it possible to reuse some of the atomic functionality from base itself. So plain LLVM IR atomics and then a post-processing pass in GPU compiler that legalizes based on which device supports what. That is the current approach, but the current reasoning, but that takes a significant amount of work to materialize. There is a prototype PR for half of that on GPU compiler itself for Metal. So if you're interested, you could take a look at that, or we could discuss what potential follow-up work could be done there by other people interested in this. Of course, the more easier fix is just to make your kernel device specific and to use @atomic from the backend itself, where currently those smarts should already have been implemented.
So we probably got time for one more question, and then people can maybe find us later or at the hackathon. If there is one more question. Anybody? All right, there's one.
I'm aware that a few years ago there were issues with pre-compiling GPU kernels, but I haven't really kept up with the state of that. Is that fixed now? Like, can I? Okay.
No, there is a bug in Julia itself that prevents us currently from accurately pre-compiling GPU code. The issue is that code is being cached when it's compiled, for example, to emit in a pre-compilation file. But the CPU caches and the GPU caches should be fully disjoint because we call into, for example, LLVM intrinsics that are not supported by the CPU and vice versa. And currently, there is a leak somewhere. So GPU code is leaking in the CPU cache, preventing us from pre-compiling GPU kernels because it might break your session. That is something that needs to be fixed in base. Once that's done, we assume that a simple pre-compile workload should work to pre-compile all of CUDA.gl. In fact, Valentin has tested it in the past, and it has worked perfectly fine. So we just need to fix one remaining bug in Julia, and we're getting close, in other words.
Thanks.
Cool. Okay, with that, and considering we all have to pack up, let's wrap it up. Thanks to all of our speakers. Thanks to everyone who came to the GPU Mini. Thanks to our awesome AV tech who put up with a lot from us. And let's all head back over to David Lawrence 121, aka the main stage room, for the closing ceremony. Yeah, did I steal your